innovation in space. I just wanted to set the scene for this afternoon's discussion and endeavoring to press the right buttons. I think all of us in the room are aware, space is expanding. It's an essential part of our infrastructure, both for our economy, for our well-being and security. We use it across a wide range of applications, communications, timing, agriculture, and of course looking at the effects of climate change and specifically natural and man-made disasters. And it's worth just, I think, focusing on what have been identified as the key challenges that can be addressed by space in the UK. We have a changing demographic, growing and rapidly growing and aging population. We want to make sure that the technology that's developing at a very high pace is available to all. We have never-ending pressures on global security and the threats of terrorism. We must understand what's happening to our climate and the environment and how we can best use natural resources to support our lives, but also ensure that we do the minimum of damage to our world. And we must create a look at how we best create wealth and economic growth. As part of the innovation and growth strategy and studies that were carried out some years ago, it became quite clear that space technology has become absolutely vital to the UK economy. Indeed, it is identified as one of the 8 great technologies, the pillars that support UK technological innovation. It's a major growth sector, currently employing around about 180,000 people in an £11 billion industry, and those figures get updated year by year and indeed grow. Our challenge as a space community, not just business, but academia and business working together, is to create another 100,000 new jobs over the next 20 years. Now, space has grown despite the pressures on the economic situation at something like 7% year-on-year real growth, about 4 times the national average. And it has clearly also been a driver of innovation in both technology, in applications, and in new businesses. And if we look at innovation in space and for space, over previous decades, the challenge of space often drove innovation here back on Earth. But actually, over the last decade or decade and a half, the dramatic advances in terrestrial, particularly consumer electronics, driven by consumer demand, has revolutionized microelectronics, and most importantly has revolutionized or brought about a revolution in manufacturing processes, providing highly capable and highly reliable technologies. And now what we're seeing is the advances in terrestrial technology is being exported back out into space, and this has dramatically changed the approaches that we can make to space, and we see this through the evolution of the wider use of commercial off-the-shelf components from this domestic market, and specifically in the development of small satellites, something close to my heart, but I'm not going to say any more because my colleague will talk about that very shortly. But if we just look at what's happening very recently, what we have seen over the last few years is the development of constellations of spacecraft, particularly using smaller scale satellites, and the conventional constellations comprising a handful of spacecraft now has developed to concepts which are talking about hundreds, even 1,000 spacecraft to provide much greater ubiquity of service in Earth observation with much more almost constant observation of our planet, and in communications, particularly bringing digital communications to those in regions where the terrestrial infrastructure is not yet in place. And so the whole concept of a large constellations is going to change the way we think of space, not least of all because the current bottleneck is access to space. It costs a lot to launch a satellite or a constellation into orbit using conventional techniques. And if we are going to be talking about hundreds and thousands of satellites, we're going to have to find a different solution to that. There are some new technologies on the horizon, such as air-breathing engines. These technologies may change the economics dramatically, but they are still a little way off and going to require very significant investment. But it is good to see that there has been an initiative in the UK to enter into this area through the intention to establish a UK spaceport, I believe, by 2018. So these will, hand in hand with these new constellations, will perhaps drive a different approach to space. So back to this afternoon. We have 4 sessions. The details are in your notes. But just to remind you, the first session is on space technologies. The second on space-enabled services, focusing on communication. The third on services focusing on navigation, Earth observation. And then, as I mentioned earlier, we will have a panel session where we can pick up general questions and any topics which we haven't had an opportunity to address. This afternoon, we have a short period of time. Each of our speakers is requested to speak for 10 minutes. After 10 minutes, the floor will open up and you vanish into the dungeons. And that will allow us to have some time for question and answers on each session, and then pick up those remaining at the end. So without further ado, it's a great pleasure for me to introduce the first speaker in today's session, Patrick Wood, who is the Managing Director of Surrey Satellite Technology Limited, and I will allow him to introduce himself and his talk. Thank you. Patrick.
So thank you very much, Sir Martin. It's a great honour to be given the opportunity of speaking here and following my boss. So I'm going to go into a little bit more detail about technology. So Martin has given you the overview of where technology, what are the technology drivers for space. So where is Surrey Satellite Technology looking at from a technology perspective? First of all, we ought to do a little bit of celebration because we've achieved 30 years of innovation in space. So a spin out from the university, we actually still have incredibly close ties with Surrey Space Centre because that's where we do some of our horizon scanning. So the university still provides that very low technology readiness level scanning for new technologies and enables us to take some of those ideas through into tech demosat missions or into early satellite demonstrations, and then we can then take those on into production satellite projects. And I'll pick up on a couple of those as I'm going through the presentation, where we've had that very early technology idea that's then been introduced all the way through into a production spacecraft. But I think it's worth celebrating that one of our successes is because we maintain very close links with academia and also pick up on those very, very low TRL ideas. So let's just reflect on, there's an awful lot of technology out there, and as Martin said, there's a lot of applications. And so a company like ourselves in Surrey Satellite Technology find ourselves in quite a diverse set of payloads and platform capabilities. And what we've wanted to do over the years is develop a series of platforms that have enabled us to mold them and adjust them and redesign them to fit a number of different payloads. And what this chart looks at is showing that for the low Earth orbit, we've developed technologies and payloads that satisfy tech demosat missions, the up-and-coming LEO comms, although LEO comms has been around a long time. SSTL did the first store and forwards satellites back in USAT 2, 3, 5 days. So, but actually now we see with modern technology, communications is becoming a much bigger driver, both in LEO and, of course, historically from the GEO market. Optical missions, starting with some of those early missions that SSTL built, all the way through from the 22-meter resolution to the DMC-3 constellation that we launched last year, which was a 1 meter resolution. So we're really starting to make sure we have that developing set of technologies for Earth observation as well as communications. Radar missions, a new one that's definitely becoming very, very new, and a lot more work is going on into it these days. Orbital maintenance. We call it orbital maintenance, but actually it's things like removed debris missions with the European Union and the European Space Agency. But we see those also in both LEO and also in MEO and GEO orbits, where people are looking for how do you get rid of the space debris and actually do that in a controlled way and an economic way. And then over the years, we've evolved from low Earth orbit into MEO. Obviously, the GeoVA mission, which was a frequency filing mission for the European Space Agency, but now obviously is part of the Galileo EU satellite navigation constellation. We've seen a rapid transition for SSTL from very low Earth orbit into medium Earth orbit. And on the very right-hand side, we see the development of the GEO spacecraft. And we have our ambitions in the future, moon, planets, asteroids. So we've got plenty of ambitions, whether it's going out to those or whether it's rendezvous in orbit. So that's going to be an exciting area in the next 5 to 10 years. What about optics? Optics have, this is following a very traditional kind of route for SSTL from the 22 meter resolution to the 1 meter resolution that we launched last year. We're actually working on a 50 centimeter design now. And you can see that there we're following a very classical innovation route from our high fidelity. But last year we did a disruptive step into that with a project called Carbonite, with a high definition video camera, high definition stills camera, and we moved the mass to an 80 kilogram spacecraft. But we weren't satisfied. That was just a stepping stone on our roadmap. And actually the red dot is where we are aiming to, which is a 50 centimeter, 50 kilogram spacecraft. And we have that in our innovation roadmap. And that'll form part of the SSTL-50 product range. And of course that enables us to also then offer products at the very, very small SSTL-12 nanosat range. I wanted to just look at some of the highlights that we've done in 2015, because I think it's not just about how we're developing our main payloads, but it's also about a lot of areas of enhancement. Terabyte payload data storage units. You have large imaging spacecraft. You are starting to collect large amounts of data, and of course you're then in need of not only storing it on the spacecraft, but also being able to then transmit it down onto the ground. Different types of thrusters, different types of propulsion system, whether it's hydrogen peroxide or small electric propulsion. All of these are necessary for those new missions where we're looking for clever, innovative ways of controlling the spacecraft. Various tech demosat missions where we've been testing high-speed data downlink. The micro-vibration was the example that I picked up with Surrey Space Centre at the very beginning, which is an early idea at the Surrey Space Centre, a PhD to actually evolve the design, went into a tech demosat mission, and we've just flown it on DMC-3 very successfully with very little micro-vibration effects in the final imagery. And a number of other examples of innovation that we did last year. One of the ones that I'm particularly excited about at the moment, given how much it rains in the UK, Tech Demosat, we fitted a RESI instrument, a reflectrometry instrument, which is measuring the reflected GPS signals from the Earth. And actually, we're starting to see some fantastic results about ocean sensing around average wind speed and average wave height, ice sensing, being able to detect ice edges, but actually the soil moisture. We just did some analysis in the last few weeks, looking at the data over the last year, seeing whether we can identify how much moisture is actually contained on average in the UK to enable the Meteorological Office to have better warning of how quickly the UK is likely to flood. And of course, other types of GNSS radio occultation and various types. Really exciting field, and it's one of the important aspects of tech demosat missions where people actually are starting to see that what we fly in tech demosat missions has real use downstream. Of course, we're also looking at miniaturization, so we're working on our integrated avionics. I'm not going to go through that, just wanted to flash that up and say, you know, historically for the previous 15 years, we've had a fairly standard stack approach to our avionics. We've gone to a card frame, single printed circuit board, and we have plenty of ideas to go to a single set of ASIC chips to do the same. Similarly with low-cost designs like Carbonite 2, where we're looking to develop the ideas of the spacecraft we launched last year, such things as mushroom cup retention mechanisms. So rather than use the standard pyro attach mechanism, use quite novel technology to do the hold-down mechanism. Fantastic example of really side thinking from an engineering perspective. It will save mass, it's much more reliable, and we're hoping to fly that on Carbonite 2 later on in the year. I think most people look at new space and they look at some of the smaller nanosats, so whether it's the SSTL-12 or SSTL-50. This chart is just looking at some of the things that we're focusing on. So we're taking the avionics that we use in our larger spacecraft, and we're looking at how we can utilize those in the smaller spacecraft so that people get the reliability that you got with the larger spacecraft actually in the nanosats. And you get the repeatability, you get the same onboard computer functionalities, you get the same avionics control. And I think from our point of view, that's a really exciting opportunity, and it flows directly from Martin's point about miniaturization, use of commercial off-the-shelf technology, and how you can use that to miniaturize, but miniaturize in a controlled way that enables you to maintain the reliability. So that was a very quick 10 minutes rattling through just a few areas of SSTL technology. But I think one of the exciting things from our point of view is it's not just in one area, it's across both the platforms, it's across the payloads, it's whether we're dealing with telecommunications, radar products, Earth observation, optical missions, but also some of those novel science missions like the RESI instrument, reflected GPS signals, and actually thinking out of the box as to how you can use the data that you've collected. And that's where some of the exciting work that's going on in Innovate UK and the Catapult, looking at big data and actually looking at some of the space data that we've already got and just how do we enhance it to get more applications out of the spacecraft that we already fly today. Okay. That's SSTL, where we are with innovation in space.
Thank you very much. Thank you very much indeed, and spot on time. If I can now introduce James Hind as Director of Strategy and Development Space Systems at Airbus Space and Defence. If you might like to say yet another boss further up the ladder.
Okay, so Martin, thank you so much for your welcome, and thank you all for the privilege of talking to you today. I guess the first thing I wanted to say is after working in this industry for 30 years, I just couldn't resist the temptation to put a few pictures of spacecraft on that very first page. And I want to start off with a link to both Sir Martin and to Patrick with that very first spacecraft, which is in the top left-hand corner. This is the Quantum spacecraft, which was basically signed off last year to bring flexible payload allocation in terms of power, pointing, bandwidth to wherever the user in a particular set of beams wants it. And it's an example of how we've had a good partnership in the UK and indeed Europe and Canada and further afield to actually make this product actually come to bear to the market, to deliver what the market wants. If we go to that middle picture, it's a picture of AlphaSat, one of the largest spacecraft ever built. Again, the payload was built, designed and tested in the UK, and a lot of the technology to go in the platform and the overall service was as well. It's a good example of how communication needs to address the need of the consumer for increased mobility, but also much greater expectation in bandwidth. And then I'd pull you down to the very bottom right of the slide, and that's a very top-level picture of the OneWeb constellation. And I know that there will be a presentation, I think, in the next session about that particular series. But I bring it up just to illustrate that innovation is not purely about technology. It's also about how can we change, how can we move with our processes, our production techniques, to build a constellation with intended spares of up to 900 spacecraft, which is like 3 orders of magnitude higher than what we typically do on a typical GEO bird. So I just bring up those as examples of technology innovation and also process innovation, but most importantly, it has to be centered in what the end market, the consumer, the government actually wants in terms of communications. So with that, I would like to give you a gift. It's very simple today. I know it's not Christmas. I would like to give you 15 seconds. And please don't use this as an excuse to text someone. It will get a little bit more interesting. But I want you to take 15 seconds to actually think, in terms of communication, what will the world look like tomorrow? And that tomorrow can be our tomorrow, but quite importantly, it also has to be our next generation's tomorrow. So just take 15 seconds to think in your own mind, your own experiences, what the world will look like. Because it's important to take that bridge and make that connection with our consumer. Thank you. So I was very worried about how to actually count out 15 seconds, and I was going through elephants and rhinos, but fortunately there is a timer here. So I'm going to bring up 3 pictures and see if you can actually resonate with any of these. First of all, we've heard a lot about connected cars. I was over at the Communication Conference last week in Washington, and there was a beautiful example from Toyota, but we can go around the world and see examples of car connection. We can read what it means in terms of updating the systems, in terms of traffic control. It's very much a product which is going to happen. So autonomy is one thing which communication can actually realize, and where satellites can play a key part. So, you know, we talk about drones, we talk about UAVs, but what we are seeing increasingly is that suppliers, retailers, are anticipating our requirements before we actually think we have them. And I think this is going to become more and more of a reality. Sorry about the image of a Starbucks. I wasn't trying to do any advertising here, but I'm just trying to get the point across how in the future we can expect, to our advantage in terms of driving efficiency and making ourselves more effective, that we are going to have that connection with retailers actually delivering. And please, forgive this next slide. It could be a man going to his cupboard to check out his clothes for the following day. But in this particular case, it's a lady, and she's trying to work out what to wear on the following day. But again, it's trying to pick up a point that through communication and connectivity, people are going to want and expect much greater connectivity, and they're going to expect it wherever they are. So what does this mean in terms of the telecom sector, satellite telecoms? I think we're going to see much more in terms of big data, much more in terms of the Internet of Things, the connection. Mobility, we're already seeing it. Once you could actually board an aircraft and think you would have at least an hour, if not 8 hours or longer, of freedom from actually connecting with anyone, and you could get on with some email, maybe writing some papers, but you don't have that luxury now. What you have is much greater connectivity to actually keep us connected with whoever, wherever we are. Again, you could go to a remote Scottish island and expect on that island you would actually get some peace. Well, that is partially the truth, but again, you have the capability today where we are starting to see much greater connectivity. Our children, and maybe us also, expect to see Netflix wherever we are. And so this is just an example of how we, as a sector, have to actually address that. So what does it mean in terms of the way we have to react. And this is just some thoughts. There are many more, and I'm very open to debate. But we are seeing a much greater need for high capacity in terms of bandwidth. We've seen a lot about high throughput systems, KA, QV, and optical, and I'll touch on that in a minute. But we're also seeing that it's now going to terabit, very high throughput systems, and that's really driving the appetite for digital processors and also for optical links. And I've just got 2 slides at the end to pick up on that. We're also seeing that there is a great difference in terms of demand. The users are moving, they want to have that power, they want to have that bandwidth as they move. And as indeed something which Quantum has done with its particular payload and with Surrey's platform, but we are also seeing it in terms of Inmarsat and their solutions going forward. But of course, it's got to be at the right price point, and that's why I bring up that issue of economy, which is becoming more and more of an issue for us to work through. We've got to revisit the core business models. No longer does the sector we serve in geo markets expect 1 or 2 spacecraft to provide broadcast. It's much more diverse than that. You're talking about broadband, still a high core on broadcast, particularly with the rollout of UHD TV, but there are still other avenues in terms of mobility which are really flexing the consumer's demand. So if we now jump to what telecom operators expect, they expect that the acquisition cost, and I stress the acquisition cost, is going down. So this isn't purely the spacecraft, this is the whole system. And it's one thing which has really benefited from what you see with Falcon 9, with SpaceX, but also what Arianespace is doing in terms of its next evolution of Ariane 6, and also to bring out the point that the whole market is evolving. So if you look at the class of launch vehicles we have today, they are sized for around about 6,000 into GEO. We are seeing a need for micro-launch vehicles which can actually launch to the tune of 200, 400 kilograms into a lower orbit. So it's actually given birth to greater elements of infrastructure to support this development. You're going to see a much greater use of capacity and the ability to adapt over time. So no longer do you have this fixed resource which you keep for 15 years and you cannot change its uplink, downlink frequency, its bandwidth, its pointing, its power allocation. It needs to move. And that is what will happen with Quantum, and it's what's going to happen with other spacecraft increasingly. I think the other thing which is very clearly a pressure on our market is that classically it takes about 2 to 3 years, depending on the complexity of the payload, to design, build, and test a spacecraft. We are seeing demands to take that down to 1.5, even lower timeframes. So the challenge is out. So how, as an industry, are we responding to that? The first thing, we're looking at reducing the cost to space. So we're looking at electric propulsion, which can either enable you to put more payload on board or take a longer duration, which will drive down the cost, the overall cost of that vehicle. We're looking at diversity of launch. Said a lot about flexibility in payloads and higher throughput. We are looking at much greater use of digitalization, and we are on the 4th generation of processors in Airbus, and we're actually the world leader in terms of exporting that product. And we're also looking at a lot more disruptive concepts. So we've heard a lot about additive layer manufacturing, but what about additive layer manufacturing in space? You know, it isn't purely about a communication environment. We have to open our arms wide to see what new space can actually bring to us as a whole industry. So just to close, I have 2 charts, and these actually come from 80 chart presentations, so I thought I would spare the rest of you the other 79 charts and just give you a flavour of some of the technologies which we are pushing at Airbus. First of all, we have digital signal processing. As I said, we are on the 4th generation and the world leader in terms of exporting this product. What we've tried to do is we've tried to actually increase the modularity of this design. So rather than taking one large processor with a significant amount of real estate, mass, power requirement, we can actually scale it now depending on the mission requirements. We've actually increased the data capacity per slice. So the previous generation would probably go up to 10 gigahertz. We can now scale this up to 50 gigahertz, but if the mission requires 2, we can do that at an economic price point as well. And this just has a very simple effect of reducing the cost per bit for mobile and actually other users. We also have the capability, and we try to show it in a very poor manner in a number of beams on the bottom right, but we have a lot of capacity which can be moved around in terms of geography, depending on where the market is. So this exactly brings out a number of different game changes from previous solutions, and it brings out a significant improvement in terms of power and mass. And I have one final chart, and then I will be off stage. It's the whole area of optical. And we've seen a lot about KA, QV developments. Let's also look at optical just for like 30 seconds. We started 16 years ago at 50 Mbps. Now, with the evolution through AlphaSat, we're at GlobeNet, which is at 10 gig. And we've seen a development of 3 orders of magnitude to get to that point, and we're pushing ahead even further in the context of EDRS. So what I've done in these charts, albeit at a fairly quick pace, is to try and show you the importance of communication, that innovation is, but recognizing innovation in its biggest sense, not purely from a technology point of view, but also from process, but recognizing the importance to address our end market, consumer and businesses. And with that, I thank you for your attention.
Thank you very much, James. My hand was twitching on the trap door, but just made it in time. And it's now a great pleasure to introduce Paul Eccleston, who's the Chief Engineer at RAL Space. We're going to change our tack slightly and now look at innovation in space science and instrumentation. Paul.
Thank you very much. Okay, thank you very much, Sir Martin. Thank you to the Royal Academy for inviting me here. So I'm going to give a brief canter through now some of the innovations that are coming up in the next 10 years and beyond for space science missions. Many of the enabling technologies are shared with those in communications and Earth observations and others, but there are some that are very specific to the science domain, which then may feed in or pull from those other domains later on. This is a chart just showing some of the missions that are already in concept, that are already being developed at the moment. The ESA program is already programmed out for approximately 10 years and beyond. Those are on here. I'm concentrating solely on those that have relatively substantial UK involvement, either in the science or in the technology and instrumentation builds. There are some one particular of interest, James was talking earlier about innovation, not just in technology, but in other areas. And in terms of business model, there's one on here, Twinkle. Let me see. Nope. Okay, no pointer. That is a UK mission that is looking at a novel business model for doing science. Rather than it being an ESA or government funded, it's looking for private investment to then produce data and monetize the data in the same way as 20 years ago that leap was made for Earth observation. So there are a number of technologies that the UK has developed over the years that are enabling those space missions. At the heart of pretty much anything is the detectors. And the UK has detector technology capabilities that are world-leading in some areas. So you can see on the left there is the Gaia focal plane array built at E2V down in Chelmsford. And also Celex, part of the Finmeccanica group down on the south coast. Their infrared detector arrays are widely used for astronomy missions. And detectors are one of the themes that sort of flows through all of the different classes of space missions that we saw earlier. Many require cryogenics. Now, this is somewhere where we start departing from the needs of Earth observation to some extent, and certainly from the communications. Deep cryogenic technologies are necessary for many of the different scientific space missions, whether it's for astronomy detectors that are operating at sub-Kelvin temperatures, or for the warmer 80 Kelvin and above detectors that are used for some of the scientific Earth observation and atmospheric science type payloads. And the UK has some particular expertise that's been developed over the last 20 years there. You can see on the left-hand side 2 coolers that have been developed at RAL, and on the right one, an adiabatic demagnetization refrigerator from MSSL that's operating down to 50 millikelvin. Autonomy. So this is an area that UK obviously has substantial involvement with the team in Stevenage developing the ExoMars 2018. Team at CISIS and at RAL Space have been involved in testing rovers, algorithms, software systems that allow high degree of autonomy within robotic exploration spacecraft, and that will become more and more important as we start moving to more ambitious missions that I'm going to talk about later. We have entry, descent and landing system expertise. There's a SME, Vorticity, that built the parachutes for Huygens and for the entry, descent, landing demonstrator that has taken off this morning with ExoMars. And deployable structures. This is an example from Solar Orbiter taken in the clean rooms over in Stevenage, but there are numerous examples in the UK and elsewhere where we're starting to look at building bigger and bigger systems in space that simply can't be launched as finally realised. And lastly, high stability structures. Often one of the biggest challenges is building optical class instruments that will stay aligned wherever the environment takes them, whether that be, in this case, an instrument for Solar Orbiter, which is required to stay aligned to a few microns, 8 microns accuracy, when it is either out at the orbit of Mars nearly or inside the orbit of Mercury at 0.28 AU, operating with extremely high fluxes coming into the instrument. And so you need very high thermomechanical stability. So looking further afield, beyond the next 10 years, what are the things that the science community would like to do, and where is that going to lead the technology innovation? I've lifted this shamelessly from work that people that are far smarter than I have done in building the Cosmic Vision program for ESA. There are 4 main themes, and this is where all of the European science instruments and science missions are going to be pushing for the next few years. They're looking at conditions for planetary formation and the origins of life. So that's exploring both within our own solar system and looking at exoplanets and exosolar systems. Looking at how our own solar system works, how it has evolved, what has caused the differences and diversity that we see in the solar system objects. What are the fundamental physical laws? This is looking at how gravity really works and trying to use space and the observable universe as a laboratory to help us learn more about the fundamental physics that governs all of this. And then how did the universe originate? How did it evolve? Looking particularly at the early universe and taking snapshots through the ages as the universe has evolved into what we see now. And so from these, I've tried to take a crystal ball and gaze maybe 10, 15 years into the future at some of the areas that will be necessary to enable a list of ambitious space missions that are sort of being touted, discussed in the very early stages over the next few years. So detectors are obviously going to be one of those, both pushing the state of the art in the wavebands that we're relatively familiar with through the UV, the visible, the near infrared, but also pushing that out into new regions. So this is an example of a terahertz detector system, which there's capability both at RAL and Thomas Keating downstairs have got an exhibition. And this would enable some new science. This is observations that have not been done before in astronomy and requires space-based systems. And at the bottom, this is an illustration of a transition edge superconductor where the UK is working on innovation and TRP contracts with ESA to develop these detectors that operate at around 50 to 300 millikelvin, where each photon that hits this silicon causes it to heat up ever so slightly. And if you hold the temperature just at the edge of where it becomes superconducting and sense the resistance, you can count the individual long-wave infrared photons that are falling on each detector. The ambitious schemes that are being developed for the next generation of big space telescopes, now I'm looking beyond JWST, which is a 6.5 metre space observatory that NASA are going to launch in 2 years' time, to beyond that. And the next generation, they're looking at things such as this. This is a concept called At Last, where they're looking for 8 to 16 meter visible light mirrors. So these would have to be shaped to a few tens of nanometers, deployed in space, so segmented primaries, and then cooled to operational temperatures of around 40 Kelvin or so. Alternatives to that exist with formation flying, and this is not the formation flying of a constellation, but this is formation flying at the sub-millimeter level to build space-based interferometers. It's an illustration of a long-wave infrared, which is probably where this would start. That's going to be the easiest application, but then long-term, the ambitious schemes would be to build visible light interferometers in space. This would give really high spatial resolution to be able to resolve objects, particularly planets around other stars. And so that is one of the options for exoplanet exploration as we go forwards. Novel power sources is another one. In order to go out to the outer solar system, you're going to require power sources which could either come from RTGs, such as this, or through large deployable structures, which can be used for many different things, including solar concentrators. If you're going beyond the orbit of Jupiter, those are going to be necessary. EDL, we know that that's in hand, but there is development needed to get higher payloads to the surface of other planets. Propulsion systems, we've heard earlier about the need to lower the cost of access to space, but once in space, the ability to get out of our own low Earth orbit, GEO, beyond is necessary, and so there's solar sails, hybrid electric, chemical propulsion, and many other options there. And building on the autonomy that's necessary to take the step from where we are now with Mars rovers traversing tens or hundreds of meters per day with ground contact between them, to fully autonomous movement of kilometers or more on the surface of other planets. Finally, we've got cryogenics, radiation shielding. This is going to be necessary once we start exploring with manned spacecraft, but also for the autonomous robotic spacecraft in the really nasty radiation environments, such as around Jupiter. Quiet spacecraft is quite key, with both EMC and magnetic cleanliness needed to allow the very precise measurements that the instruments want to take. Laser systems, both for communications, but particularly once you get into the outer solar system, communication is going to be key. And some of the quantum technologies looking for high accuracy gravity sensing, for example. So finally, this is a list of some of the mission concepts that I know about or have been involved in that are being thought of and proposed for the period between 2025 to maybe 2030, 2040. Whether that be the big astronomical observatories, formation flying, probes to the outer solar system, to Uranus and Neptune, exploration to near-Earth objects to return samples from Mars, or even fly through the plumes of Enceladus and return those. The Europa mission that is already on the books at NASA, whether there's a European involvement there, and some of the other more ambitious schemes, such as putting radio telescopes on the far side of the moon. Thank you very much.
Thank you very much, Paul. We now have an opportunity to take some questions from the audience. So I would ask our two previous speakers to join Paul and I on the stage here.
Therese Corey, Beecham Research. You said at the beginning of your talk, the last speaker, I'm sorry I've forgotten your name, there might be some cross-fertilization between these long-term space missions, but also terrestrial applications that are in use today.
I think that was you, Phil.
Yes. Yeah. So there's a number of areas there. There's the optical communications is clearly one of the areas where the telecoms industry, it's one of the potentially large disrupting changes that is going to be necessary to evolve that, but also for getting high data rate data back from the outer solar system, for example. The New Horizons probe that's flown past Pluto is taking about 8 to 10 months to return the data at very, very low data rates, not even approaching dial-up. Also, autonomy. Some of the autonomous systems that are being developed for rovers also feed into agritech. For example, there's rovers being developed for crop monitoring and health monitoring in the environment.
Any other questions? Right at the back.
Hi. I was just recently at a workshop up in Lancaster University where they discussed last December's flood event. The electricity went out and all communication failed. And this led to serious problems for the police, hospitals, utilities, and it was all about communication. So I'm just wondering, in your talk, you were sort of looking forward to the sort of advantages that more communication can bring. Is there anything that can be done to really add resilience to our communication systems?
Yeah, I think there are a number of things, and we can take the advantage of basically government work over the last few years. First of all, if you're talking about a physical event, such as a flood, such as a tornado, something which knocks out the communication infrastructure. I think what we're seeing now in terms of systems which can mobile, which can change their coverage, can change their allocation of power, that's something which can benefit straight away. So I think that's a tremendous advantage. Another area, of course, is recognizing that the world is indeed a friendly place, but there are people who do not want to be so friendly. So the capability on the spacecraft also has to be ruggedized and resilient to some of the threats which are out there, both in terms of the satellite itself and also in terms of the coverage, in terms of the uplink or the downlink. So there are other aspects of actual technology which we're onboarding onto more and more commercial spacecraft to actually give them that resilience. The third point I would bring up, which is quite important, is recognizing that all of those features have traditionally been strengths which our government military forces need, but increasingly we're seeing that there are governments and other agencies which also need that capability. So we're trying to make sure that that technology is spread forward as well.
Whilst we wait for any other questions, I'd like to just propose to our panel if they could each just make a short comment. I mean, we've seen how miniaturization has changed the way we approach space. It's provided us with wider opportunities. We can see how big data, a horrible phrase, but it sums it up, I suppose. Big data and the Internet of Things is going to perhaps make what already is a big challenge, and also is going to change the way we view our world. And we see this as spinning out in terms through Constellations and other applications, novel approaches to services. So services have existed, of course, for a long time, but now we're seeing some different approaches to services and business, and we've heard a little bit about some of the opportunities that are coming up on space exploration. But one of the things I'm interested in is to try and identify, are there some key technological hurdles or challenges that we're going to face if we're going to sort of break through into the next generation of these capabilities? Are there some key technological challenges which we've really got to address if we're going to dramatically increase throughput or dramatically reduce cost of launch or access and to orbit? So whilst my colleagues here, having not told them about this beforehand, think about that, does anybody else have any other questions that they would like to address?
I think mine was actually a little bit related to that. Margaret Harris from Physics World magazine. My question was based on Paul's presentation, but could be answered by anybody, I think. Of the enabling technologies you mentioned there, which of them is the most challenging, poses the most challenging, or is the most underdeveloped currently compared to the others?
Probably from the space science perspective, the driver for any instrument and any mission is always the detector. So the detector sets are what you build the capability of the mission around. Often you pick the best available technologies for everything else around you and use the state-of-the-art detector, and that sets what science goals are achievable at any point in time.
I mean, if I could sort of just press you a bit more on that, because what specific technologies do you think are impeding detector advances that we should be focusing on? Sorry to put you on the spot.
So I think the key thing is expanding the wavelength coverage, particularly into the long wave infrareds and into the terahertz regions, where at the moment there is limited capability or there's limited heritage. Everything through the UV, through VIS and near IR, that would be evolutionary changes rather than anything that would be a step change.
I think from my point of view, it's sort of feature size of devices. There's a huge awareness on the ground of the evolution of processors, how fast they're becoming, how large data stores, and people expect that technology to be transferable into space. And I think that's one of the big challenges, which is how do you take these small feature size devices and use them productively and constructively in a low Earth orbit, medium or geo or beyond. And it's, of course, that's down to the radiation susceptibility of those devices. So I think that for me, at a particular low-level technology, is how do we identify technology that's more robust, that enables us to use the commercial technology, but actually use it in a space environment.
And if I could be equally awkward, are we already approaching the shall we say, the smallest feature size that's going to be practicable? And if we are, what's the next step?
Yeah, but every 5 or 10 years, if I'd been asked that question, I'd have said, yes, we are close to it. But so my answer is no, because over time, we have managed to go to smaller and smaller feature sizes. And I think sometimes that's about understanding the technology in more detail and understanding how we can use those devices in a space environment to give them more protection. So, I think we are seeing that kind of curve going to smaller and smaller feature sizes, but and there's no doubt we will see some of those improvements.
I don't know how long you've got to answer that question, so I'll mention. Okay, 5 minutes. That's good. I'll try and do it. No, not for me. Okay, I'll try and do it in 2. I think the biggest challenge, I would say, is recognizing who we are, and what I mean by that is, again, if I give you the example of myself, I've worked in the industry for 30 years. I can tell you how to build, how to test a payload, aspects of how to operate a spacecraft in orbit. I can think how my customer wants to use that spacecraft. But our first challenge is to actually recognize how our next generation and that generation after that want to use our spacecraft and the features which we want to use, the things we want to explore. And, as I think a good few of us in this audience realize, working in space is great fun, but it does also represent a challenge. So it's trying to be forward-looking would be one of the aspects I would bring out. The other aspect I would bring out is what I think either Sir Martin or Patrick represented, is SSTL is an example of 30 years of heritage. The industry is a little over 50 years old in terms of actually getting spacecraft into orbit, going to various places. We can do it, but we have to have a forward-looking vision. The third and final point I would bring out, and I think I'm on my 2-minute slot, is the fact that the end market is still expecting communication, the service we provide in observation to improve, and they're still expecting the quality, but they want it for a lower price point, and they want it quicker. And that represents a huge challenge, which I would finish with.
Thank you. Just going back to your question, Martin, of different types of technology, although I was answering the sort of small feature size from the audience question, actually laser communication terminals, one of the challenges is how do we get those small enough to work on low Earth orbit platforms? Because if we think about what that will do to the architecture, you'll be able to then communicate from GEO back to LEO down to UAVs, aircraft, and it will radically change how we perceive getting data out of a low Earth orbit spacecraft constellation. So I think for me, one of the really exciting changes that's happening at the moment is laser communication, but low cost, and watching that technology development curve with the megabits per second going up to gigabits per second, and at that point we get to a usable step change in technology.
Thank you. Yes, sir. Can you stand up and then wait for the microphone? Thanks.
Nico MacDonald from the Research and Development Society. I'd be interested to know in what innovations are going on respectively in how you conduct R&D, who you collaborate with, and models in which you collaborate, and perhaps timescales as well.
Okay, I can start. Of course, one of the things we're trying to do in a large organisation like Airbus is recognising the strength which we have in-house in terms of the heritage over a number of years. But the other thing which we're trying to do very strongly is recognise that innovation is very broad. So we've got a couple of examples now where we have actually gone out to small to medium enterprises, taken designs where they maintain their IP and actually supported them in actually bringing that product through to a point of space qualification, which still today requires a lot of work to go through the various qualification demonstration steps. So it's trying to really embrace partnership with small to medium enterprises, but also what we're trying to do now, and it's very good that we've got Helen Newby, who is the head of innovation on the front row as well, is recognizing that we need to actually open our arms wide to include universities and look how we actually work with universities and moving technology forward at that level as well.
Yeah, so with RAL Space, we sit in a slightly different environment, coming from the quasi-governmental organisation. So we have always historically partnered with the academic community quite strongly, but we are more and more supporting industry and trying to play a supporting role in enabling other people's R&D, both through the SMEs, but also enabling the big industry players in the UK, both in their research and development and in their main programs.
And I think from my point of view, it's not only continuing a diverse engagement with academia, but it's also SMEs, exactly as James mentioned, because I think that there's some fantastic ideas out there, and sometimes those small to medium enterprises do struggle to get those ideas, but it's working with them in a way that actually enables them to develop their ideas and keep their IP. I think that for me, and also some new emerging companies like Goonhilly Earth Station Limited, who are trying to open up access to use some of their facilities. So it's again working with those and coming up with novel ideas as to how you exploit those kind of capabilities.
Thank you very much, gentlemen.
Okay,
Brilliant. Thank you.
Thank you very much. That brings us spot on time. Just as a few concluding comments on that. I mean, I think that adding to that last question, we're going to see increasing international cooperation, particularly as new nations become active in space, developing their own interests and their own particular focus on what's important to them. That will give opportunities for increased cooperation and a cross-fertilization of ideas. And then coming back to the question about what's in the big next step, I think we're going to be seeing an increased pressure on how we manage the human-machine satellite interface to make that as effective as possible. And then as we push down feature size and we increase speed and we're trying to reduce power, then trying to get the synergy of not just the electron and photon based, but perhaps even the biologically based systems and biomimetic systems, we will see an increase in that, and this is going to raise new challenges. So that brings us now to our second session, and thank you very much for the speakers on the first session. The second session is also on space-enabled services, but this time focusing on some of the innovations in satellite communications, and I'd like to invite Tony Azzarelli, who's the Vice President of Regulatory Affairs in OneWeb, which we've already heard a little bit about, and we'd very much like to hear more.
So thank you for today, and I want to present a little bit about OneWeb, what we're doing, where we're going. From this slide, you'll see that we're going to have a global connecting system, and the vision of OneWeb is basically to have connectivity affordably for a lot of people around the world. We know that from several sources that more than half of the world is unconnected today. And this is a problem because a lot of countries are trying to grow economically and also educationally as well. And you'll see from this chart, for example, that the developing world is lacking connectivity up to 70%. And, well, it's not just the developing world, but also the developed world. If we go a little bit closer to us in Europe, about 20% of the homes in Europe do not have super-fast broadband. The UK is in the 6th place with 90% of connected homes. Even as we go to the UK, Ofcom's report last year in 2015, you see that super-fast broadband is missed in about 70% of homes in the UK. And that's super-fast broadband. Of course, if you look at the lower speed broadband, that's going to be less, of course. But still about 2%, 3% of homes today do not have any broadband at all, even at 2 megabits per second. So why is that? It's because fiber costs. Deployment of fiber to homes, especially in the rural areas, costs a lot of money. Where there's less populated people around, it costs about $4,000 a kilometer to just lay fiber. So imagine you have homes 10, 20 kilometers away from the main city. That's going to cost a lot of money just to get people connected to the internet. And that is also a cost to growth. We talk about growth in the UK. Well, that's quite important. About 50% of SMEs from the Ofcom report, I think I've seen, 50% of SMEs do not have broadband connectivity today at good speed. So OneWeb. OneWeb design has been completed. We are looking to deploy by 2020 648 satellites initially at 1,200 kilometer altitude, which puts it in the low Earth orbiting constellation. Each of the satellites is about 150 kilograms, about 1 cubic meter each. So not a nanosatellites, actually it's much bigger than a nanosatellites, but still quite small. The orbit is a circular polar orbit, nearly polar orbit, about 87.9 degrees inclination. And we're going to have 18 orbital planes with initially 36 satellites per plane. Of course, one of the important features for the user is high elevation angles from the perspective of the antennas, which will be deployed globally, means that no obstructions to the satellites, which you may have in other cases. And more importantly as well, latency. The round-trip delay of data is less than 50 milliseconds, which puts it nearly to the same or similar delays that you would get with your ADSL internet today at your homes. Coverage-wise, each satellite will cover an area of about 1,000 by 1,000 kilometer surface. The satellite capacity as a minimum, we're going to be offering about 7.5 gigabit per second over that area. Globally, that's going to go to about a couple of terabit per second of capacity throughout the world. Of course, we can't do this without partners, strong partners like Airbus. We have initiated a joint venture with Airbus, and James this morning, just earlier, mentioned innovation in processes, basically. We are trying to basically redefining satellite manufacturing here. We're going to be mass producing the satellites, these 1 cubic meter satellites, improving cost and schedule. And of course, the disruption there is that each of those satellites is going to cost less than $1 million each, basically. That's quite an innovation, quite a disruptive feature in these kind of satellites, and Airbus is with us on this venture. So initially, we're going to manufacture about 700 satellites, which are going to be deployed by 2020. And the factory in Toulouse has already been put into place to initially build the first 10 production satellites. We signed one of the biggest contracts with Avionics last year in June. We're going to be deploying 21 Soyuz rockets from French Guyana, Baikonur, and another facility in Russia. Each of those Soyuz rockets can fit as much as 32 spacecraft, which will be deployed over a period of 18 months, approximately one every month. In addition to that, another strong partner we have is Virgin Galactic. With their rockets and airplanes, we're going to be able to deploy, inject directly into orbit one satellite at a time. We have 59 Virgin Galactic rockets and 21 Soyuz rockets in this contract. Of course, the biggest challenge for us is the ground segment, and Qualcomm is helping us into defining the chipsets and constructing the boards which will fit into satellite antennas, which are about 50 centimeters size each. And the interesting feature from Qualcomm is that they have succeeded in this technology because they're going to be mass-produced, as well as the fact that the millions of processes per second each chip has to make is enormous, because of the fact that we have to track the satellite from the user terminal and be beam endovers on the same satellite and also across satellites as well. That feature is quite important and quite challenging, and Qualcomm is basically working on this chipsets. Our markets are basically, as you see from the slides, the majority of services and users will be on the sort of broadband connectivity side, using Ethernet through connecting to our terminal, connecting homes and schools and hospitals, of course, SMEs, and then near to that on the ground as well, cellular backhaul. Cellular backhaul because, again, there's a lot of people across also developed countries which have no connectivity even with their mobile phone. In addition to that, the vertical markets are also as important, actually even the more lucrative, in effect, connecting people on the move in ships, airplanes, and trains, and as well as we will be able to help governments even on the provisions of PPDR, which is Public Disaster Relief Services, emergency services as well, using OneWeb as a backhaul communication to those communications, so emergency service communications. That's the way we envisage the system to work. We will not require any specific terminals for users. The users will be able to use their own devices, their own phones, tablets, laptops, and those laptops and devices will be connected either through Ethernet or through a 3G, 4G LTE connectivity and Wi-Fi through the user terminal of OneWeb, which from the user terminal through the satellites and the gateways, they will connect to the internet or to other places through the gateways on the Earth, basically. In terms of data speed, we can offer up to 50 megabits per second to each terminal, and there will be a range of speeds depending on the requirements. And of course, as I said before, the important feature here, because it will make it even possible to backhaul cellular connectivity, our latency is less than 50 milliseconds. That will enable a lot of these kind of services, basically government, e-medicine. It's possible now to actually interact with doctors across different regions. E-learning, e-commerce, of course, e-offices, teleconferencing, cloud computing, e-games. And as I said before, our main vision is to actually connect those people which actually require that communication, require that connectivity today, which is not there for them, like in rural areas and remote areas, basically. Of course, in addition to the fact that OneWeb is deploying their LEO constellation, we are going to work closely with companies and partners like Intelsat, integrating the LEO and the GEO solutions together. And that sort of solution is now undergoing epic. Intelsat is right now deploying their geostationary satellites, and over the next couple of years, we will integrate also OneWeb, and the whole structure is now being developed at the moment. We cannot do this without partners and investors like the one we have on the slide. Oops, that was fast. You see we have big companies in the manufacturing side like Airbus, HNS for the ground infrastructure, operators like Intelsat and Grupo Salinas in Mexico, for example, as well as Bharti Airtel cellular operators, and Virgin through their investment and also the launchers as well, Avionics as a partner, Qualcomm for their chipsets and their technology knowledge. Of course, we have other companies like MDA in Canada for the antenna design for satellites, as well as Coca-Cola for service provisions across the world. Basically, a lot of people ask me the question why Coca-Cola is because they're a brand which is known worldwide, as well as they're actually a big service provider which can provide our services even in wherever they reach, basically. And I'm done. Thank you.
Thank you very much indeed, and spot on time. So we have an opportunity now for you to ask some questions before we take a break for coffee. And just to remind you, if you can stand up and announce who you are, and we'll start over there and then come to you, John.
Phil Beavis from Telespazio. Can you say something about the association between the terminal and the satellite? Is it one-to-one or one-to-many or many-to-many?
Yeah, the terminal of the satellites will be one-to-one.
Okay.
Yeah.
So there's a small time when the dish will have to switch to a different satellite.
Yeah, we have several designs for the dish. It's not just the dish; it could also be a phased array antenna. And actually, our main design is a phased array, which actually the switch is going to be quite instantaneous. For the dish, there are single dish or double or two dishes depending on the customer, depending also on the market as well. So you're right; it will take some very small time to switch from one satellite to the other, and then also depending on the solution as well.
Okay, and it's duplex. Is it full duplex?
It's duplex. Yes.
Thank you.
Thank you. John Forrest, 21net. We're a company that provides internet services on trains. This started out with satellite access in a variety of countries. In the last few years, people have said, oh, no, it's all going to be 4G, 5G. You can forget satellite. However, there is a view in the US that says it's going to be all of those. You have got to lay your hands on every bit of bandwidth you can. And I'm very interested in your hybrid solution. We've seen companies like Amazon and Google reinvent the way we do a whole variety of things. Do you see OneWeb as another of these sort of companies that will revolutionize the way we communicate?
Well, we hope so. As I said before in the presentation, the whole vision is actually to try to connect those people which have no connectivity today. And it's not just the developing world, it's also the developed world as well. We see nearly 20% of people in the EU that don't have that connectivity. We're talking about tens of millions of households which don't have that connectivity. So how do we get there? The other thing is that Google or the other company, Facebook or whatever, they're big companies. We will get there, but it's going to take time. Not maybe as quick as they did. And we're trying to help also those companies to actually, not those companies, those people to get access to Google and Facebook and so on, that don't have it today. But not for the social benefit as well, but also from the growth perspective. A lot of people, even commerces, basically schools and medicine, a lot of people in the world don't have that sort of facility. They have to travel miles and miles to get to those kind of facilities. So our biggest goal and aim is to help people. But of course, to help people, we also have to make the money to help them as well, because the constellation costs, the technology costs as well. So yes, we will, do our best to actually be disruptive in the technology, but as well as you've seen it, we have to also work together with the GSO. We have to also work together with other kind of constellations as well, because we can't do it on our own, basically. Chris.
Hi, Paul Monks, University of Leicester. I'm very intrigued that at one point you said about merging the GEO in Masa with your LEO constellation. Can you tell us what value you derive from that? And also, one of the things often angled at SATCOMs is latency. Do you have any solutions in your OneWeb solution to the latency type issues?
So the value we get from the sort of GEO, and in this case it's Intelsat, is actually they have the customers. So we tap into basically the customers that they are having today, and this sort of synergy where we need to sell our services. We need to actually provide our services to people, while they have also their infrastructure, their customers as well. And of course, on their side, they need us to actually provide that sort of low latency side of connectivity as well. And as I said before, we don't think actually we're going to put aside GSO, geo type solutions. We need both basically. The geo are very good in the high trunking. They have high bandwidth, high speed. We actually have the low latency. We have the smaller terminals, the lower power, for example, which you can connect almost anywhere you think of, basically. So the two actually go hand to hand together, and that's why Intelsat decided to actually working with us, and we basically drive and get benefits on each other that way.
Chris McIntosh from Viasat. Tony, what's the biggest technological challenge that you face right now?
Biggest technological challenge that we face today is the user terminal. The satellites are very simple. Actually, I didn't mention this before. We are gone from O3B. In fact, Greg Weiler was the founder of OneWeb, was also the founder of O3B. We managed to go from a satellite like O3B, which is big, with about 30 kilometers of cable, into a satellite which is small as 1 cubic meter with almost no cable, basically. So the satellites are very simple. They are transparent at the moment. Maybe second or third generation might go into a different, more complex satellites. We might actually need laser communication, more cheaper laser communication to do inter-satellite link eventually. But the satellites are very simple. They've been designed. Also, ground segment is very simple. It's the user terminal, the gateways, and the ground segment together needs to be actually worked out more finer and better. So the technical challenge is on the ground rather than actually in space. Of course, the other challenge we'll face in the future after the first 600, 800, 900 satellites we're going to launch is finding launches which actually cost less and also are capable to actually launch multiple satellites as the one we found with Soyuz, basically. So that's another challenge we will face in about 5 years or 10 years time frame.
Question there.
Richard Wild, Thomas Keating Limited. Perhaps a silly question. Is congestion, and I don't mean one satellite hitting another one, when you've got this number up, is that a trivial problem or a proper problem?
So we managed to solve that issue of, let's say, collision even between our own satellites by designing the orbit in a way to avoid the two satellites will never come any closer than about 50 to 100 kilometers basically from each other. And that's basically at the poles. You'll find this at the poles. So from the perspective of the satellites in the same constellation, we'll solve that problem. And from the perspective of actually where we place the satellites in orbit, we actually are in a place in the orbit which actually has the least amount of debris which exists today in space, basically. So we are going through a very high debris place, which is around 700 to 800 kilometers, to about very low debris place, about 1,200 kilometers, basically. The satellites have been designed and will be actually manufactured to have electric propulsion and the capability to deorbit when they reach end of life, basically. So that's we want to be very clean in space and have sustainability space in a way that actually leaves space affordable for other constellations, other people, and other companies as well. So we are very careful in that perspective, basically.
But in terms of RF, radio frequency, I mean, it's no faster now to walk around or to get in a cab in London than it was 100 years ago. Is there a problem with RF interference and so on? Do you have all the bandwidth you need, which doesn't interfere with other people, perhaps competing countries constellations?
Okay, I may have misunderstood your question. I went to debris instead of interference from RF. Yes, in fact, we have the whole process, and that's why I work in regulations and in RF regulations in a way. There are international rules that we have to comply with to actually ensure that other operators actually do not get interference. One of the biggest challenges is the GSO protection, for example, from non-GSO. So we are within the limits which are affordable by the ITU, the International Telecommunications Union in Geneva, which have been in place for the past 15 years, actually, those kind of regulations. And it gets to show that Intelsat and EchoStar, which is HNS, is part of EchoStar, are our partners, and if they had any small issue with that, they would have let us know from the beginning, basically.
I think we can just squeeze in one last question before coffee.
It's just a quick one. I think you covered it, but what do the radio astronomers think of this?
In what sense? From which perspective?
From noise, interference. I mean, it's going to be quite different to have as it were, a complete curtain around the Earth, nowhere to look through.
So from the perspective of radio frequency interference, the radio astronomy use of frequencies are actually quite far away from where we are. And in that perspective, there is no issue. We haven't heard any of the radio astronomers have any issues with that. And all of this is actually then managed to the ITU, the International Telecommunications Union. When you want to put a system like that, like GSO in effect, you make your own satellite filings, and they are there for other countries and other operators to see and check if they make any interference with the existing systems, basically. So I've done this before. I looked at radio astronomy myself before when I was working for Ofcom, and I know where they are and what we should look for example. So we have no issues in that respect, basically.
Thank you very much, Tony. And I'd like to, this draws to conclusion the first two sessions, and I'd like to thank the speakers for their contributions. We're now moving on to our penultimate session. Again, this is space-enabled services, but this time focusing firstly on satellite navigation, and then after that on Earth observation. So to give us some thoughts on satellite navigation and applications, I'd like to introduce Dr. Chaz Dixon, who's the Deputy CTO of the Satellite Applications Catapult.
Thank you, Sir Martin. Good afternoon. Now for something different. Navigation. Where are we going with navigation in this century? Satellite navigation includes satellites, a ground infrastructure that supports those satellites, and that is necessarily global because the satellites are in MEO orbits and therefore rotating around the Earth, and a user segment. And this is all about delivering positioning, sometimes known as navigation, but navigation is different than positioning, timing, and velocity. And then a whole load of services that benefit from location awareness. And timing. Don't forget timing, because this will give you timing more accurate than almost anything else. This will give you tens of nanoseconds of timing. Everybody wants a GNSS. The Americans started with the GPS system, which has been fully operational for 20 years now. They switched off a deliberate degradation that was considered a risk to national security 15 years ago, 16 years ago in fact, and the system is currently being upgraded. In that time, it's been continuously fully operational. The Russians have a very similar system that came in slightly after the GPS, and again is a global system providing positioning and timing with very high accuracy. Europe is creating its own. This is intended to be operational this year. This is providing a whole array of new signals and services and will be the world's first non-military GNSS. And yes, you did hear me right, non-military GNSS. So the American GPS that you rely on for positioning in your smartphones is entirely reliant on space military hardware from the US. And the Chinese, not to be left out, are producing Beidou. Beidou has been operational regionally for a little while now, and its global operation is coming. That's not enough, though. There are regional systems. The Japanese have a system, the Indians have a system, and many people have an augmentation that improves the integrity and the accuracy of the system for specific needs. And typically those are safety of life needs, things like aviation. And Europe, America, Japan, India, and Russia all have those space augmentation systems. Why is GNSS interesting? Well, since we're in the Royal Academy of Engineering, I thought the first thing to do was to look at an engineering perspective on why this is interesting. And that, as I guess, I don't know how many of us here are engineers, I guess a significant proportion, it's complicated, and engineers like complicated things. This is complicated. The systems are complicated, there are complicated subsystems, right down to complicated components. The service offerings are also complicated. There are standalone systems, but there's also augmentations for accuracy and integrity by satellite or by terrestrial systems. The mobile phones have their own augmentations to acquire a much more rapid time to first fix. The products are complex. There are simple receivers which themselves are complex integrated silicon devices, but the products also integrate multi-source communications, GIS, or maps to those that don't know what a geographic information system is, multi-technology communications, IT, human-machine interface, and other sensors. And there's complex maths and physics needed to make it all work. So those of you that have done engineering, physics, maths degrees, your time has not been wasted, because all of that stuff on orbital dynamics right through to general and special relativity is important to make a satellite navigation system work. And after all that, as if that wasn't enough, it turns out to be useful. Revolutionary accuracy, positioning, timing, speed leads to demand for products and services, which leads to growth in business, in jobs and careers for engineers. But engineering isn't quite enough to run a world. There's a financial perspective. It's a huge market. It's hundreds of billions of market with huge growth. So 11% is a widely accepted figure for the overall growth of downstream GNSS applications. And why? Because it is incredibly cheap, providing incredibly good accuracy. It is available globally 24/7. You can get a position fix, a timing fix once per second. If it's interesting to you because you have a high dynamic platform, you could have 20 fixes a second. It's super reliable, and in some cases, integrity is augmented by additional systems. And therefore, society uses it for all forms of transport, for location-based services, for tracking of people, things, for critical infrastructure, for timing of communication systems, banking transactions. So a quick look at where we're going. I'm going to look at 3 sectors very rapidly. So in 10 minutes, there's not long to look at these. So the ITS market is another tens of billions of market. And the important things here are congestion reduction, pollution reduction, improved transport efficiency, reduced infrastructure costs, and things like safer roads. There's some legislative support to that, and whilst we're part of Europe, then a lot of these come out of the EU. And personally, I hope that situation will remain for some while. And then we integrate those systems with vehicles, LBS in things like smartphones, to create robust, resilient positioning and communications to support road pricing, perhaps not a popular topic, but flexible traffic management, reduced infrastructure costs, and the communications between vehicles, the sharing of information. So that's more of an infrastructure view. From a vehicle point of view, there are advanced driver assist services, things like adaptive cruise control through to semi-autonomous lane control and automated platooning of vehicles. That requires position, speed, and acceleration information that is incredibly accurate, that is very highly reliable, all of the time, everywhere, communicated and shared amongst the vehicles in a timely manner. And the solution, perhaps, is carrier phase GNSS, which can give us centimetric accuracy, augmented by gyros and accelerometers, wheel tick devices, and parallel sensors, things like radar, LiDAR, machine vision, because we need to navigate in tunnels, urban canyons, underground, where satellites are not visible. But local collision avoidance is not a job for GNSS. Fully autonomous vehicles are coming. Maybe they need the same. Maybe they need exactly the same. They might need a little bit more, and that's an open question right now. They also need machine intelligence. And then there's a question of societal acceptance, which is well beyond the scope of what we can talk about today. Next sector, the enormous sector of location-based services, LBS. This is more than half of the GNSS downstream sector, and growing incredibly rapidly. What the chart there is a collection of a few different market surveys and analyses, and all of them agree that this is tens of billions per annum of market, and that it is growing incredibly rapidly. The precise numbers differ, and if you're from a marketing community, feel free to argue about that, but the big picture is enormous market, enormous growth. Dominated from a hardware perspective at the moment by smartphones. 3 billion smartphones exist. The hardware is miniaturized silicon, integrated with IT, with communications, with a human-machine interface, with other sensors. But that's not enough. You then need an application to go somewhere, find someone or something, to track a thing, to advertise. Location-based advertising, advertising that is aware of your location and your movements, was reckoned to be almost a billion market, almost £1 billion market in 2013, and growing dramatically. Location-based gaming is in its infancy and projected to be enormous again. But that's not all of the story. Wearables are a coming technology, so we're just starting to see sports devices which have a lot of the same technologies but integrated into a different platform. They will have new apps around them, new services on them to support your sports activities, to support your health, to track your kiddies or your granny. Here we're less interested in the extreme high accuracy of carrier phase, but multi-frequency, multi-GNSS, using all of those constellations is exciting. Using the new services coming with Galileo, like the pilot tone that let us navigate in more difficult environments, augmented by miniaturized gyros and accelerometers, supported by signals of opportunity from communications, from TV, etc. And something else is going to give the indoor solution. People are pushing GNSS as far as it can go, and it really struggles for indoors, and it really fails for underground, and something else will come in that space. Finally, there is a new breed of users coming, and they're not human. We will have deliveries onto our drive, according to Amazon, brought by machines. We will have robot weeders. They're not going to position the weeds by GPS, but they're going to position themselves within your garden by GPS. And what are the streetlights doing there? Well, how do you report a failure in a streetlight to the robot that's coming to fix it? Do you look up a thing on a database and have an interface with that database, or do you relay the location of that streetlight? And if the sensor is cheap enough and you have a communications mechanism, you would be crazy not to do the latter. Thank you very much.
Thank you very much, Chaz. And now it's a pleasure to introduce Dr. Samantha Lavender from Pixelytics, and also chairman of the British Association of Remote Sensing Companies.
So I'm now going to transfer us over to the Earth observation area. And there are huge developments also going on in Earth observation. We have the unmanned aerial vehicles, or drones, that have been mentioned several times before, that are being increasingly used as platforms. We also have greater numbers of satellites and satellite operators. And this is changing the way that satellites are being launched and the availability of the data sets that are out there. But in parallel with the small satellites, there are also the large satellites still being launched. And in Europe particularly, we have the Copernicus program that is launching the Sentinel series of missions. And this is a very long time series of satellites with multiple satellites of each mission type. So we've already got a radar mission and a high-resolution optical mission, and very recently a lower resolution optical, thermal, and altimetry mission. And they're just about to launch in April the next SAR mission. So we will then have 2 satellites with the same design in orbit, increasing further the mission data. There are also the idea of taking some of the missions that are currently on the polar orbiting satellites and putting them on geostationary missions, so that rather than waiting for your satellite to come round and go over you, it's always situated over you. And this is very useful if you're particularly interested in launching a satellite that's really focused on a particular area and getting continuous coverage. So with a geostationary mission, you can take imagery something like every 15 minutes. There's LiDARs in space, so this is optical systems that are actively sending out laser pulses and receiving signals back. There's increased resolution, so for many years you would be looking at data and seeing something very blurred, and increasingly that's no longer a problem. And there's, to go alongside this rapidly, exponentially increase in data, there's more automatic techniques. It's no longer possible to look at every image that is coming out of a satellite. You just cannot keep up with downloading it and viewing it like I did in my early days of my career when a mission called CIRRUS was launched. My job was to process that data, and I used to look at it every day to check it had been processed correctly. And there's a question, though, that remains about who is going to pay for all this data. How is it going to be funded? So for the Copernicus missions, everyone in the room is paying for that data. As taxpayers in Europe, we have all contributed to the funding of those missions. Well, and that data will be freely available for people to download and use. And this was something that in some ways was started off by the Landsat program that is operated by the USGS in America. And I particularly like the quote I've got up there. When they were trying to sell that data, they couldn't sell very many images. And it wasn't because they were particularly expensive. I mean, I know some operators in the past have tried to charge you several £1,000s for optical data and went bust doing it. But they were down at a few £100 for images. But still, it was only tens of thousands of images that were being downloaded and bought. As soon as they made that data set freely available, they rapidly hit the 9 million mark. And what they argued in order to allow this to happen and justified it afterwards was actually the American government was already paying for these satellite missions. And actually the amount of money coming back really wasn't worth the effort in trying to collect it. It was much better to make that data freely available and get the wealth of everyone using your satellites, which then justifies more of them to be launched. But that's not the total solution, because there's only so many missions that can be funded by governments. We also need a commercial marketplace as well. My other little bit in there was just about data size, really. So if I want to download a Landsat 8 image, it will be about a gigabyte in size. With a Sentinel-2 image, I'm now up to 7 gigabytes. there are ways of now dealing with this, and it's not really a single image, Sentinel-2. It's actually lots of little images, and you can download them. But actually, that's still not easy to do unless you know what you're doing. And so most people still download the whole thing and then throw the bits away they don't want. The other element I wanted to bring into this is the marketplace in terms of who is working in the Earth observation sector. And for this, I'm using a few graphs that come out of a recent report, which was an industry survey that's recently been undertaken and is regularly undertaken by the European Association of Remote Sensor Companies. And I've just included these two figures because for me they were quite enlightening and interesting in that if you look at the distribution of employees within this sector, most of them are in the smaller companies. You're looking at a sector that is dominated by small and medium companies. There are large employers, and there are people like me that are micro-employers, but it's these small to medium companies that are the real employers. And also, in terms of growth, it's the smaller end of the market that's growing rapidly. So this is, as has already been mentioned by some of the speakers, the real need to have this support for the small end of the market. But equally, if you browse the accounts of these companies, and I did it in advance of this talk for all the UK Earth observation companies, most of them are losing money and not actually making profits out of doing Earth observation. And they can do that because they've got nice, rich parent companies, or they're small one-man bands who are really just paying their salary. So we need to have a way to finance small companies and allow them to grow into bigger companies and bring on employees. And there are several ways of doing that. And I'm going to use myself as an example. So I set up the company Pixelytics now just over 4 years ago. And this is our growth curve. And this is from a website called companycheck.co.uk, which I find quite useful for browsing other people's accounts and seeing what they're up to. But you can also actually now, Company's House has a beta site where you can download all the accounts for free if you want to go into great detail. And it's useful to do this just to try and understand how people are running their companies and making money or not, which we all need to do if you want to survive in the long term. And you can see we're small. We're at the micro end. And in my first year, which was a partial year, I didn't do great and I made a loss. As I assumed I was going to get money in, and it didn't materialize, as often happens. But since then, we've been growing and making a profit every year. And actually, this year, we're still finalizing our figures, but our turnover will have increased by about 80% plus, and we'll have made a profit of £15,000 to £20,000 on a turnover this year, which has been about £120,000. And we've made a decision, a purposeful decision in this company, partly from my previous experience and partly from my like to be in control of things, in that we are self-funding ourselves. We have decided we don't want external shareholders. And there are positives and negatives to having external shareholders. The positive is they come with funding. The negative is that stops at some point, and if you're not profitable, they may well shut you down. And as my little quote in the right-hand side shows, most companies who don't attract venture capital fail within 3 years. And this is quite often companies that might have got some venture capital at the start, but haven't really worked out how to make a profit. And so after that 3 years, the venture capital disappears, and they shut down. And there was a company I know very recently who I was trying to work with who had a big turnover of several £1 million. They were growing rapidly every year. The parent company in America failed 1 year to make decent profits and decided to do a cost-cutting exercise and shut them down within a week without them being able to argue about it. So there is this real need to understand business models. And SMEs, I think, have a very important role in that they have this specialized knowledge and experience that is not always readily available elsewhere. And although universities can play a role in commercializing research, actually many of the academics in universities want to do academic research, and that's why they're in a university. They don't want to spend their time doing commercialization. So having small companies that have come out of academia and now are trying to create this profit commercializing research can work better. And one of the roles I play in larger companies is to be an in-house scientist for them. So if they need a scientist for a few days who will work on exactly what they want for those 2 days, I will go in and do that as long as they pay me a sufficient amount of money. And that's one of the ways I make the money to keep my company going alongside selling the Earth observation and product services. And that will mean that I will often be a lot more responsive than an academic professor who will have lots of other responsibilities, of which it won't be to bring in today's salary. So my conclusion is it's an exciting time in the field of remote sensing, and there's a wealth of data, but being used by non-experts as well as experts. But we've got to work out how to turn this into a viable market that can make profits and grow the companies. And so my question that I'm going to leave you with is, how do we transition this delta that we have into viable space services that are making profits for those companies, so we can then invest back in the hardware and launch more satellites in the future? Thank you very much.
Hang on, and we'll bring up. Thank you very much, Samantha. I think it's certainly true to say that it's very difficult to make money out of data, but you can make money out of the value-added services, and information and actionable knowledge is where the value lies. Now, we have a few moments for questions. Who would like to kick off? Well, I have one whilst you're gathering your thoughts, and that is, there's been a reference to the public sector and the private sector in Earth observation, and I suppose also to some extent in positioning and navigation services. And the question here is, how do we get that balance right? Because yes, the government uses our tax pounds or dollars to invest in space hardware, and therefore it's reasonable for that, the results of that, the data that comes from that, to be freely available for exploitation by the taxpayers. On the other hand, does government want to, or governments wish to be responsible providing that hardware ad infinitum into the future? And if not, how does the private sector enter into the upper part of the upstream in order to relieve the burden on the public purse, in which case they have to be able to make money out of the data and the services they provide. So there's a bit of a balance to be struck there, and I'll be interested in both in terms of navigation through Galileo is a very good example, and then perhaps later on Earth observation, just a few comments on how you might address that.
I'll start, because I have an answer which is not a Galileo answer but a GPS answer. I think it was between 8 and 10 years ago that the US assessed the tax revenue from GPS civilian products and services, the tax revenue in the US only. And the tax revenue was more than had ever been invested in the whole military program to create GPS. And bear in mind, GPS is primarily a military system and is of the order of 4 times more expensive than the civilian Galileo system. So 8 to 10 years ago, before the market had truly grown to its current size, the tax revenue on services and products from that state-provided service was sufficient to justify the creation of that service. And if private industry had been astute enough to create that system and then smart enough to gather the tax revenues, huge profits were available.
I think there's different types of satellites for me, really. I mean, you've got the large, very expensive Earth observation missions, that are there to provide very stable, long-term data sets with as small an error as possible. And they are very expensive to launch, and you can only launch so many of them. And at the other end, you have these very small, nimble satellites that are there to provide a service. So a lot of the venture capital-funded satellite missions are basically photographs from space. If you look at the calibration, it starts to often get quite ropey, and it's very difficult to derive something scientific from that. So you have those two ends, and then I think the difficulty is working out where the middle point is, where the crossover is. And this is where the Copernicus system is currently causing some difficulties, because it's at a resolution where some people were or have been trying to sell commercial products, and now they're competing against free-to-access products. And I think now they're being launched, we can't do anything about them, they're free to access, but we have to ensure that the users of the eventual information don't think that's free as well. Just because the satellite data is free, the information product's free. Someone has to process them, and there has to be money generated downstream from that process.
Thank you very much. Any questions from the audience, or do you wish to challenge any of those statements? So you're going to wave your hands a bit because it's a bit dark up here. So.
All right. I have a question about to what extent this the statement on the slide there about transitioning to a viable space industry, to what extent is it specific to remote sensing, and to what extent is it a problem for the space industry as a whole? I mean, we heard from Sir Martin earlier that the UK's space industry is worth £11 billion per year, but I have heard rumours, maybe scurrilous ones, the rest of the room will tell me, that some 10 billion of that is from Sky TV subscriptions. So I don't know whether there's a more general problem here, whether it's specific to remote sensing.
I would say the rumours are not scurrilous. It's the way the statistics are calculated. Sky TV is considered a space company, and so their revenue is in there. But I mean, I wrote it as an Earth observation statement because that's my area. But I think it does apply to space more generally in the UK, in that we've gone through a really great period where we have a UK space agency and increased funding for space. But there needs to be a proof that this is bringing those tax revenues back to the government for them to continue investing. So there is this real push to find a way of both making money and proving that we've made money from more than Sky TV.
I'm not wishing to enter into any scurrilous discussions, but I think it is quite plainly that the downstream, i.e. the services, contribute at least 80% of the revenues, and the upstream is responsible for about 20%. And one might argue over the detail of those figures, but the ratio is probably about that. But unfortunately, without the upstream, we don't have any downstream. So you've got to look at the totality of the business. Chaz, do you want to put your head into the scurrilous discussion?
I haven't got much to add. The first company that I ever worked for in the GPS arena made receivers, and unfortunately, the Challenger disaster delayed the American. There's many unfortunate things about the Challenger disaster. One of the unfortunate things for me was that my company was making GPS receivers, and the GPS program was delayed. So we sold the business. We sold that business entirely to an American company, in fact. And as I presented in my slides, we're talking tens of billions of downstream exploitation. So space is often slower than its terrestrial counterparts in achieving revenues, and there's a more complexity. And as Sir Martin said, the upstream is absolutely necessary, or there is no downstream.
Thank you very much. Well, now, Richard first, and then Peter.
Richard Brooke. The Earth observation data is rarely of itself sufficient to provide an information service solution to an end user it usually is going to have to be combined with data from other sources and other sensors, and indeed interpreted with knowledge of the context of the end user's requirement. That's quite a challenge. Have you got any thoughts on how we should address that challenge?
I would say that's what's exciting, actually, and why I love working in the field. It's something we do all the time, and it's has to be a collaboration between the end user and the satellite data processing company, because both hold data sets and both hold different amounts of knowledge. So when you develop a product or a service for a customer, you don't just develop it and hand it to them and expect them to like it. You develop it along with them so that they gain a better understanding of the errors and uncertainties in the satellite data, and you get a better understanding of what they can and cannot accept in their final product.
Peter?
Very quick one on user charges. I was involved in the very early days of GPS, and about the end of the 70s, I was invited to go and give a talk at a Signal conference in Brussels. And I went over and explained that I thought user charges, which is what they were considering at the time, were a very bad idea. I came home. What I didn't realize was that the US customer had then got on to ITT headquarters. I was working for a subsidiary of ITT, and explained to them that because ITT were building most of the payload, they didn't think it was a very good idea for someone, some minor irk from their subsidiary, to go around trashing their ideas.
I have some sympathy with that from my own experience. However, I think one other point is that, of course, if we look at back over the last 100 years, communications has always been a paid-for service. Everybody's been very comfortable with paying for communications, whether it be originally from telephones and then eventually satellites and then handsets and so forth. But what we haven't been very used to is paying for Earth observation and also for positioning services. And so I think there's a question of heritage in terms of the public mind as to what they perceive as being something they should pay for, and something that somehow has come out of either a scientific or a military environment where it's sort of free to use. That brings us to the conclusion of this session. Thank you very much indeed, Chaz and Samantha. And it brings us now to our final session, which is going to be a panel session. So if I could ask our panelists to make their way up to the front and take a seat. We have five seats, so we hope we have 5 panelists. In no particular order, we have Craig Clark, the CEO of Clyde Space, Paul Febvre, the Chief Technology Officer from the Satellite Applications Catapult. We have my colleague, Professor Gao Yang from Surrey Space Centre, Space Robotics, Catherine Wheeling-Jones from the UK Space Agency, and Professor Paul Monks from University of Leicester. So the formats for this particular session, which is scheduled to take probably about 45 minutes, is first I'd like to ask the members of the panel just to make a few introductory remarks, introduce themselves very briefly, and then to highlight some of the questions that they would either like to see or feel are burning questions that we should be addressing. So just a couple of minutes each, and then we'll throw it open to questions from the audience, and if you don't have any, I've got some very taxing ones to throw in. So let's just go down the line. First of all, Paul.
Hi, good afternoon. I'm Paul Monks from the University of Leicester. I'm a professor of Earth observation science, but also have a number of different roles. I'm also a co-director of the UK Space Agency Centre for Earth Observation Instrumentation, so I have a view on the upstream, and I'm also a regional director for the Satellite Applications Catapult Centre of Excellence for the East Midlands. Wow, they're long titles. For me, the challenge is space-enabled services. People are data agnostics. People don't really actually care where data comes from. They only want a service. I think the challenge for us and the innovations really allow about developing a value chain for that and recognizing where the opportunities are in that value chain. I think if you were to talk about, as we're in the Royal Academy of Engineering, if you were to talk about engineering challenges, for me, many of those are maybe around digital and digitally enabling that innovation. I think that Microsoft this week announced they're going to open 4 new data warehouses in the UK. Data will live in the cloud, and you will access that somehow to deliver your service. So for me, that's much about where the innovation is going to come from. It's going to be innovation about using data in ways we've never really thought about, from satellites that we probably won't really care where they come from. They've still got to be good, they've still got to do the job, and they've still got to innovate. But for me, they're some of the challenges that lie in the future.
Thank you, Paul. Paul Fevre from the Satellite Applications Catapult, background in telecommunications. I entered the realm of the innovation space because of the fascinating opportunities in all of these other satellite services. I think for me, one of the things that characterizes the satellite domain, and in fact any technology domain, is that the pace is relentless. We are continuing to see dramatic changes in capability and performance. And that's really quite imperative. Any organisation that doesn't recognise that and doesn't try and take advantage of the latest technology is going to be left behind. Any particular market continues to expect better services all the time. And those organisations that don't adopt the technology and innovate to actually address that need are going to fail. But it's also true to say that any particular market has a limited capacity for providing the wherewithal, the funding to keep the community going. So the markets, the satellite technologies are only going to be able to grow in terms of the communities if they address new markets. We've heard today a number of presentations about the potential new markets. I think the whole aspect of autonomy, whether it be vehicles or beyond line of sight communications for drones, or for in fact digital health, those kind of aspects now of where you take your life into your own hands, if you like, and live in the community. We've got an aging population that's empowered to do so, create enormous opportunities that for organisations that will be prepared to service that need. And those are the growth areas. However, in order for that to happen, we need to be leveraging the innovation that takes place in those communities, and we need to be engaging in those communities. So the key thing here is make sure that we understand the regulatory frameworks, how they change, and the technology frameworks, and make sure that there's an awareness about how satellites can really change people's lives in the future.
Thank you, Paul. Craig.
Hi, I'm Craig Clark. I'm the CEO and founder of Clay Space. We're based up in Glasgow. We've been involved in small satellites and CubeSats for 11 years now. One of the first companies to be involved in CubeSats in the world. I think from an innovation point of view, it's a really interesting time for space. I'm seeing it from a slightly different perspective. I was in California at a conference, a new conference on small satellites and applications and investment a couple of weeks ago. There were some really interesting new companies out there. There's a lot of money getting into space at the moment, and that's getting into lots of new innovative ideas round about product and data product rather than actually investing in the technology. So going back to some of the comments that were made earlier about the UK Space Agency and UK government needing to see a return on investment in tax being paid by these companies that they're putting their money behind at the moment. In the US, they don't talk about that. They talk about these new companies like Planet Labs and Spire actually returning on investment to their investors. There's billions of dollars going into space in the US. And there was talk about this drying up. I was talking to some people recently, they think the funding's drying up. But actually, from my experience in the last couple of weeks, is it's not drying up. There's lots more companies out there that are getting funding, doing new and interesting things. It's not all about visible or Earth imaging. I was talking to some people looking at long and medium wave infrared imaging from small satellites and data products based around that. The Internet of Things and communication is going to be a huge market for small satellites. So for me, innovation is not necessarily about the technology. In the space industry, we talk a lot about technology. We focus a bit too much on that, but it's on the end user. The end user could be actually, one of the guys that was there made a very interesting point. The FTSE 100 companies, talking to those guys, talking to them about how space data can make their lives easier and how we can put products together that can service their needs. So there's lots of opportunity, and it's up to us to make sure we make the most of that.
Thank you, Craig. Catherine.
Okay, hello. Catherine Mealing-Jones. I'm the Director for Growth at the UK Space Agency, so a slightly different perspective again from some of the other panellists. Absolutely pick up this idea about the user and the market and the purpose in mind, whether it's public good or wealth creation from innovation in the space sector. I think there's a real issue about breaking down the barriers between sectors. We've talked a lot about the space sector this afternoon, but quite a lot of the growth needs to come from the spillovers into other sectors, and how do we do that? And in terms of the focus, are we using challenges and prizes enough to crystallise the questions that we're trying to answer? I think there's a question about how we build on some of the strengths we've already got, for example, through things like the Regional Centres of Excellence work, which we're now partnering with the Catapult on, and the role of incubation in innovation and driving things through to market. I think there's a question for us about how we highlight hidden gems, use spare IP, that sort of thing. There's a lot of things that are created that are just left hanging, and how do we actually get something productive from that? Speaking from a government perspective, I think it's very important that we get the regulatory attitude right so that we can support experimentation and innovation, allocate scarce resources in a way which maximises innovation in the space sector. I think government has a big role in innovating itself in terms of its use of space data and services. So we've got the Space for Smarter Government programme, but what else could we be doing? Could we be procuring differently? I think there's a whole area where government's role is not so much about funding, but about a lot of the other aspects of our role which support innovation in the sector. I do think there's a real issue around skills. So we're talking engineers, ICT specialists and so on, data modelers and so forth. But I think picking up on one of the things Samantha raised in her presentation, I think there's a real need to match the people with the ideas up against the people with the business models and the business innovation skills in order to drive value creation and the right kind of innovation. And finally, I think there's a whole sort of developing area around data about the economic value of the space sector. So we had a challenge to the size and health, is it all just B Sky B? We're redoing or doing the next survey of the size and health of the sector this year. It'll be very interesting to see what comes out of that. But I think, this isn't just for us in the space sector, this is for investors all over the place. This is for people in other sectors looking to see whether they can draw value from our sector. And this is also part of the case to support any further government investment in this area. And these are all part of the backdrop to innovation. So I'll stop there with those thoughts.
Oh, thank you, Catherine. Yang.
Very good afternoon, ladies and gentlemen. My name is Yan Gao, a professor of space autonomous systems at Surrey Space Centre of University of Surrey, also known as the birthplace of SSTL. So I think it's a culture in Surrey that we innovate, we inspire, we bridge the gaps between academic research and the commercial exploitation. To talk about my own field, which is in robotics and autonomous system, I'm actually very satisfied and pleased in terms of the recognition of innovation in my field, because this is reflected very clearly by the talks that has been already given by a number of industrialists in the afternoon. So I think this is not something academics generally are worried about. But what we see, I think, in the area, probably also transferred to other domain of research, is the real opportunities to work very in depth with our industrial partners, the opportunities of real missions that we can fly some of these novel ideas. I'm actually very pleased that though this afternoon we don't have a dedicated talk in my research field, but several talks have actually recognized robotics and autonomous systems, related technology underpins those key sort of futures and future missions that would fulfill our human ambition to explore, to utilize, to improve our daily life. But it's very useful if we can materialize some of these ideas, these ambitions, through a very coordinated process in terms of flagship missions, for example, then people can see where they can contribute. I was very excited. I don't know if people are following news this morning, but the European ExoMars mission, the first phase 1 of ExoMars, was actually successfully launched this morning. Of course, the follow-on phase 2 would be a rover mission, which UK sector across the board, including academia and industry, play a crucial role. So fingers crossed, if the phase 1 goes very well, and then we can very safely to say we have that follow-on mission in 2 years' time. I think that sort of mission, we really appreciate. We can have more of them, if possible. I think, of course, from our perspective, we can say sometimes it takes really long time to see such a mission opportunity to actually arise. I remember 10 years ago, I was involved in a phase A study of this mission. And at that time, the mission was scheduled, I think, in 2008. So we are talking about 10 years delay of such an innovative mission concept. So I really want to engage the audience, hopefully this afternoon, and hopefully get some enthusiasm or hopefully support in the time to come to come together and to work together for a more rapid mission and realization of these missions in the days to come.
Thank you, Yang. Well, I think we've heard from quite a wide cross-section of academia, from government, and allied laboratories, and also from the small SME sector, identifying a number of sort of topics. How do we handle big data? How do we make sure the data is useful for the end users? It's the end users that are driving the markets. How do we address these new markets? How do we make sure that we stimulate both the commercial and the public good sectors? Space, of course, is a multidisciplinary activity. It's becoming even more so, and space robotics and autonomy is going to play, I think, an even larger role in the future of space, whether it be in exploration or in on-orbit assembly, for refueling or for debris mitigation. So I think we can see a very wide range of activities here. I would now like to open the floor for any questions. Again, if you can just raise your hand initially and then stand up and announce who you are. And I'll try and keep my eyes open and make sure I catch everybody.
Yeah, John Auburn from RIA Group. I'd like to ask the panelists, we're going through a lot of European focus in the next couple of months in terms of whether we remain in the European Union. We're having to prepare the case for the next ESA ministerial. So I'd like your views on how we can, assuming we stay in Europe, how we can get the most out of ESA, the EU, to help the UK build more business, to be more innovative, to influence their programs, especially now with ESA having XSAT at Harwell, and how we can work more closely with them in programs like IAP to get the best for the UK PLC.
Thank you. So rather than ask every one of the panel to pronounce on this, can I just ask you in the panel to raise your hand if you think you're well suited or you have a neat riposte? Catherine.
Yeah, I mean, it's a really important year, isn't it? We're going to see the European Union referendum, but actually internally in the UK we're going to be very focused on preparations for the ESA ministerial, and alongside that hopefully the refresh of the MOU that we have with ESA about the future of XSAT. I think we've done a lot in this country to try and increase our influence in the European Union and within ESA, and that's something we will look to build on this year. We're already very engaged with the European Commission as they formulate their new strategy or policy document, which they'll be publishing in the autumn. But I think that's something that we could do as a whole community more. And certainly through the preparation that we do for CMIN and through the engagement that we have through the European Affairs Group, for example, with UK Space, and through our advisory committees and things to the agency, I think we should have a real focus on how we get more out of those groupings. It is certain that we gain a lot of advantage here in this country from membership of those different bodies, and I think we should be looking to do a lot more to get even more back than we do already. So I think it's a sort of call from me for input and collaboration around the preparation for those things.
Anybody else with a burning response? Yes, Paul.
Thanks for the question, John. I think from our perspective, Europe, whether we're in or out, is always going to be a really important partner for collaboration for UK industry and academia. And I think it is an important year, but I think what we need to do as a sector is really look to how do we engage not only with our space partners, but also with organisations that are going to be key for the potential future of the whole space industry, whether that be the transport sector or the health sector, digital health, for instance. So I think the European Commission has a large role to play in terms of generating the opportunities for the space sector to actually provide significant contributions, and it's up to us to actually recognise that and take a significant position in terms of actually engaging.
Thank you. Just hang on for the microphone is approaching.
Hello, good afternoon. My name is Jocelyn Loma, and I'm an MD of a SME called Sereno. I sort of see the whole space platforms and the terrestrial platforms as a little bit like a giant brain. We have knowledge centres around the world, which are the neurons, and the communication media between is the synapse. And my question for the panel is, how does the human-machine interface or the synapse affect the functioning of the brain?
Paul.
Okay, so I'm going to have a go at that quite challenging question. I'm going to turn it around slightly and say that I think that the dreaded big data has 5 V's. Yeah, I'm going to see if I can remember them: volume, variety, veracity. I wrote the last one down. Velocity. Now, the reason why I say that, because that's essentially what you're saying. And actually, I think the challenge really is the 5th V in that, which is to derive value from it. So we can have a lot of data out there, and we can make putting data together a goal. But unless you're trying to derive value from that, you don't build a brain just because you've got a brain. You build a brain because you want it to control something, which is the human body. So I think, in a way, for me, that you've got to find a way of deriving that purpose, and that purpose will help you design the way that you put those structures together. So I guess I'm giving you a wider view, really, of that.
Thank you. Anybody else wish to rise to that challenge? Other questions, please.
Eleni B, Head of Innovation at Airbus Defence and Space. When we look at the development of what is called new space in the US, I'm quite astonished, actually, by the important role played by NASA at the very beginning and still today in that development. Based on the current model we have in Europe, how do you see, you both on the government side or also on the private side, the role of the European Commission, ESA or national agencies to boost new space in Europe?
Craig?
I think it's actually, it does look from the outside that NASA play a huge role and influence in new space, but they actually don't. It's just that they're so big that the small number of people that have an interest in new space are able to actually contribute a little bit. So the number of missions that have flown that are small satellites in the US, for example, is actually fairly low compared to the amount of money that they put into space. It should be a lot more. So actually, but it's not really that different to Europe. I mean, we do see quite a few small satellite missions now being actioned by the European Space Agency. They're a little bit different, maybe have a different focus, but there is support there already in Europe. It's just that the new space market is moving so quickly just now. The big organisations are just that are government funded just aren't able to keep up with the pace. So most of the money that's going into new space is private money to drive that along.
And I mean, I think there's a real temptation for governments to try and get involved in something that's got a big buzz around it, like new space. So we see this with the Commission, we see it a bit with the European Space Agency. I think it's important for the actors to take their appropriate roles. I think, you know, it's very entrepreneurial, as Craig said. It's very fast developing. It's funded differently. And I think the questions government needs to ask, whether at the European level, or, you know, the global level, or at the UK level, are, you know, how do we facilitate this? What are the threats and opportunities that it poses? And how do we respond to that? So I think we would perhaps go more into our role as a regulator, you know, our role in spectrum allocation, that sort of thing, in order to facilitate the market and look at those threats and opportunities. I don't think it's a rush to funding and programs, personally.
Can I just put something else in there? I think it's quite interesting. The whole new space context moves, especially Earth observation, from essentially satisfying some of the scientific markets to potentially satisfying some of the emerging commercial markets. I mean, if you look at it from a perspective of a commercial business, actually timeliness is really critical from the perspective of actually driving a business proposition. So it's not very helpful just to have statistical data because it doesn't change very often. So if you want services which are going to generate information that's actionable, then actually timeliness is key, periodicity, actually updating it. So I think that's where new space brings some significant potential. I think one of the key challenges, though, we have, and touching on Paul's point, with a big data challenge, if you like, as the sensors improve and the number of satellites improve, we have an effectively explosion of the amount of data that can be generated, and yet the information in that data is still quite sparse. It's quite hard to extract the value. So if we were to look at sensors as being generating a huge amount of data, you've got other factors which come into play. The cost of storage, for instance, and the availability of high-capacity storage is a key factor with regard to how do you enable the use of some of these sensors. The cost of processing falls all the time, and the cost of communicating the results, the information. And as those actual different dimensions change, those different attributes, it moves the sweet spot. What should you do? Should you process at the source to generate information products? Can you do that in a way that's sufficiently flexible that allows enough people to be interested in the outcomes? And I think one of the questions that Samantha was raising earlier, which is, the interesting thing is to find that conjunction of the data that can be available from satellites with the data that could be available from elsewhere. That's very helpful unless it doesn't scale. If it requires a specialist solution every single time, then we need to have thousands of people working in the sector to address all the different opportunities. And I think one of the real values of GNSS, in a sense, is that for the mass market proposition, the baseline product is good. There is still a value proposition for high quality, high value services on top. And we need to get into that arena with the Earth observation technologies as well. And I think then we will see the blossoming of a new market.
Actually, I know the question was not targeting academics to answer, but I personally really think this brings out a lot of new opportunities, for us to very rapidly implement and materialize new concepts. Going back my sort of enthusiastic voice earlier about, the mission seems to be implemented in a slower pace than, of course, scientists like myself would like to see. So, for example, there's this new business model like Kickstarter, which we see a lot of university-based, ideas can be very quickly implemented, accumulate attentions from public. I think, personally, I can see a lot of this particularly advanced concept, for example, doing something with robotic technologies, autonomies in orbit, or even going planetary missions such as going to the moon, can be probably quite rapidly implemented through this sort of means. So I would clearly quite, encouraged by this.
It's actually a good point. We haven't heard much about Kickstarter type approaches to business, but I guess that's perhaps the ultimate end of that part of the scale. Other question. I tell you what would be very good. It would be very helpful if you can put up your hands in advance of asking your questions, because then I can sort of identify you. Gentleman in the corner under the picture.
Nico MacDonald from the R&D Society. I just picked up on an interesting comment I think that Craig made which was innovation isn't about technology, it's about the end user. And I think, Catherine, you agreed on that, which I think is, in this sector particularly, is a novel observation. But I would observe, having worked in the digital industry for 20 years, that we've been talking about this on the web and mobile and so on for that long. And there is almost a sort of inverse correlation between user focus and innovation. And often if you focus on the user, you don't actually innovate, because the truth is people don't know what they want. Nobody knew they wanted GPS outside the military and logistics. Nobody knew they wanted Facebook, before Mark Zuckerberg created it 12 years ago. So I think we just need to be wary about that. And I'm interested, Craig and Catherine, what you feel you've learned from the digital sector about focusing on the user so that we don't make the same mistakes twice.
I suppose that's another version of build it and they will come.
That is one version of it, yes.
Catherine, do you want to first?
Yeah, I suppose I distinguish between the user and usefulness. I think if you develop things, you've got to understand what your purpose is in doing so. I think some innovation needs to be better at explaining how it could be utilised. So, I mean, some of the talk earlier was about actually developing products and services with the user alongside you. I think there's an earlier stage than that where you're thinking about what the utility of the innovation is. And I guess my observation would be about being very clear how you would use the technology in a different way. There'll always be happenstance things that spin out, and I don't think you can kind of arbitrate for that. So I think, innovation has a number of aspects, but I think in general, understanding some sort of utility that you're trying to develop is an important aspect, and then whether you've got a user alongside or that comes at a later stage is another sort of point in the development process.
Craig?
Yeah, I mean, I think it's a little bit different in the space industry. Apart from the geocomms market, where there was a clear commercial need and that's been very successful, most of the space industry has been about developing spacecraft and making prototypes. So we haven't really got to that stage where we're then mass producing those spacecraft. So we're starting to see that a little bit now, when it's more product focused than just one-off technologies. But I think there's some really good examples coming out now where people are joining up the dots. So they're seeing the technology, they're seeing the application, the product with the data, and then the end customer. And a good example of this was a company called Omni-Earth. It's a startup company. They managed to put some data sets together for a water utilities company, a massive company in the US. And it was an important set of data for this company. It was because they're a startup, they don't have that much regular custom. They're kind of feeling their way a little bit just now. But they sold this data set for $20 million in a week. The customer came along, put the data together, sold it for $20 million. So they're exploring those markets, and I think we're going to see a lot more of that.
Yeah, I must be in the wrong business, aren't you?
I mean, I think there always is in space disruptive innovation, and I think that's always happened, and especially on the technology side. But there is another model, and maybe it's just codifying what Craig says in some way. Everybody talks about spin out and spin in and spin out. Actually, in space, a lot of the time you see this pathway, what I would call spin along. You spin it in space technology, then you spin it out into something else, and then you bring it back into space technology. So the innovation ecosystem in space is not very linear, you team that with disruptive innovation, then actually often try to get focus, which users can give, drives this. So it's not a totally rational place, the innovation landscape, in some ways.
Thank you very much. Jonathan. There you go.
Jonathan Seville, University of Surrey. I spend a lot of time with the terrestrial telecoms companies that are developing the 5G standard. And they talk at the user end of the operation about a lot of the same things that you've talked about this afternoon. Are you in competition with them, or are you in collaboration with them? And if you're in collaboration, is it collaborative enough?
Shall I take that one?
Dick's yours.
Keep reaching for the mic, but I'm forgetting that it's a wireless one. The wonders of wireless communications. I think from the perspective of where we have been and where we need to be, might be two different things. When we look at the competition for spectrum, for instance, to satisfy what is potentially anticipated as the significant need for the society as a whole, satellites community has access to a lot of spectrum that's actually viewed with quite considerable envy, shall we say, by the terrestrial cellular sector. But we've also got to recognise that actually rolling out terrestrial communications to provide completely ubiquitous coverage is actually a very expensive affair. And this is where satellites potentially can play a role. If we look at 5G, some of the market perceptions, there's a vast range of anticipated markets, including some of the very high bandwidth, very low latency technologies for in-room coverage for gaming, for instance, which is possibly an interesting market, but it's not something that the satellites are going to be relevant to. Satellites, in effect, are much better, as we know, about the wide area coverage. I think one of the considerations here from the business model is what are people prepared to pay? And there's a sense of what you can pay and what you're prepared to pay for your communications capability, whether it's your broadband at home or when you're on the move. And it's, from a consumer perspective, it's in the order of £30 to £50 a month, something of that nature. It's not going to go up to 500. And what we see in the telecom sector, if you look at the rate of change of innovation and the cost per bit is a good metric. In the satellite arena, over the last 30 years, we've effectively improved the cost per bit by about 1 order of magnitude every 8 years. It's about 10,000 times cheaper now than it was 30 years ago. In the mobile sector, it's about once every 4 years, so it's 10,000 times cheaper than it was 15 years ago. Now, at some point, it ceases to become interesting, the cost per bit, because it's ubiquitous. You're not going to measure it in bits terms. It only costs you a few cents or a few pence to do something useful. And in which case, the driver for innovation, for change to improve, starts to diminish. It also means that if you think from an applications perspective, if you've got a commercial need to do something, you need to transfer a certain amount of information to drive your business. At some point, it becomes cost effective to do so. And if you don't do it, somebody else will take your lunch. And this is where I think where we're seeing a convergence. We're seeing a convergence in terms of the business opportunity from satellites, provide wide area coverage that's complementary to the terrestrial cellular coverage. And it's complementary both from a capability perspective and from the cost perspective. So I think there is a time ahead where we do need to be working together with the 5G community, and satellites should be part of that mix.
I'm very happy, by the way, if you want to challenge any of our panel, if you disagree with their response, please feel free to stand up and succinctly challenge them. The lady who had a hand up just over there, thank you.
Hello, my name is Hong Mei He from Cranfield University. Our research is particular for cybersecurity for manufacture and information intelligence. So I have looked at, listened to your several presentations and you're talking about the space-based service. So I'm thinking about currently IoT technology has been popular topics, and IoT security also is a popular topic. I'm sure the space-based service we combine with IoT technology will be flourished in the future. So I'm thinking about cybersecurity might be a very important topic in space-based service. How do you think?
Thank you very much. Actually, it was one of the points that I jotted down a bit earlier, and that is, as space becomes increasingly embedded in our infrastructure, and we correspondingly become utterly dependent or increasingly dependent on it, how do we ensure that we have the necessary cyber resilience, if you like, to make sure that we have a comfortable existence? So rolling all those together, Paul.
I'd like to add another one to cybersecurity, which is one of my V's earlier, which is the veracity as well, which is I think that a system that grows with data from space must also have something that quality assures that data. So I think that the two key challenges there are the truth of data, the veracity of the data, but that's also linked to this cybersecurity problem. And I know that the car manufacturers are spending a lot of time at the moment to make sure that the cars of the future cannot be hacked. And partly that's driven a lot by the data flow in and out of a modern car. The telemetry that will come from it in the future will be much greater. So this is actually a real challenge, I think, for us. And I know it's brought to the fore by some of the newspaper articles at the moment about encryption, the role that encryption will play. So I think the cybersecurity has a number of different layers to it. It's absolutely critical for the truth and the resilience of services, but there's a whole regulatory area about how governments deal with encryption that may be a barrier to the market in the future as well. So I think I'd turn over to Catherine to comment on the regulatory angles of encryption and whether that would be a barrier to market. That's a horrible thing to do, isn't it?
You're up, Catherine.
Anyone else want to say anything? No? Okay. I mean, yes, I mean, it clearly is an extremely important aspect in the provision of space services and space infrastructure, and something that I think, there's been a lot of focus on over the last few years with the publication here of things like the National Space Security Policy and much more sort of government focus on all of this. I think a few things sort of help. Some of the major systems, I'm thinking about the European systems, have security and kind of assured service absolutely baked into them, and it's something that I think ultimately things will kind of find a level. You'll have systems which are highly assured and systems which carry a bit more risk, and you'll sort of have to take your choice amongst that. I think for government, I think things like regulation can play a part. Standards, space standards and data standards are very important. And the kind of categorisation of certain bits of space infrastructure as critical national infrastructure also sort of help. But I think ultimately it's something where industry, users and government have to sit together and work out what the best possible balance is here, because it's very easy to design systems which are so encrypted and so secure that they're highly assured, but then obviously that pushes the price up, makes it a barrier to market, as Paul says, and so on. So I think, there are some sort of famous examples of where security has been a real issue in space sector services, but I think we're still finding the right level. And I think ultimately, probably, you'll get to a situation where something like the way that people are looking at Galileo, where you've got kind of, an open service and then different layers of assurance of service, is probably the way that some of these bigger systems will develop. But I think it's a very important point and something which is needs to be balanced out between the different parts of the sector, really.
If I could just put one thing on the table. If we think classically about the threats and risks to satellite services, and historically, it's primarily been about the electromagnetic aspects, effectively the interference and the threats that come about from being able to challenge that. That's an external threat. Cyber is very much more internal. It's much more insidious. You can have a latent threat that's ready to activate at any time. I think as we have more intelligent processing and perhaps processing of satellite imagery on the satellite because of the necessity, I think we've got an interesting time ahead with regard to assuring integrity of the information that comes off the satellite, because it won't just be raw data anymore. It will be something that was processed, can be assured about the process. I think from the aspect of the considerations of availability, which historically jamming and the like was good an issue. Now you've got the aspect of, can you disable entire systems? How do you ensure that the system is there when you need it to be? And I think that we really as an industry need to actually start to adopt some of the key technologies because the threats are going to do so. I too agree with you.
Just try to add from an academic point of view, this is clearly very important. I just want to speak up the fact that a lot of academic colleagues of mine, which I'm aware of, all over the world and in Europe, are actually setting up working groups to look at those standardization procedures that, with a vision that there are all these cross-sector issues. For example, I know colleagues from Surrey, including myself, have been contributing to those discussions within those working groups, for example, for European Cooperation for Space Standardization, as well as a non-space standardization organizations such as W3C. So all these organizations, I think, as far as we are aware, actually pay quite attention to this issue. That's why they are having those working groups, which might be contributed by the academics to begin with. But I think in due course, they will introduce industrialists, people who are going to write procedures for those standards to formalize what the scientists would recommend.
Martin, can I add one more thing in this area? Sorry. I think we talked a lot about autonomous systems today as well. And I went to a seminar last week and I hadn't really realized how far autonomous systems had got. And I think you will see autonomy, because autonomy actually drives down price. So there's a market pressure on that. But I think autonomy and cybersecurity, they're a heady mixture of a real future innovation challenge. As we go to more autonomous systems, we're going to need more assurance of those systems against those sort of things. So I think I'd like to add that kind of brave new world vision to the mixture as well.
And I think there's also going to be questions that arise as we get more autonomous, indeed more automated as well, as to the liability regimes that go around it. And it's not just, if your auto drive car crashes into another one, who pays for that? It's if we have Earth observation data which is processed and then passed on to a user, and that user somehow suffers damage from it, who is liable for that? And then that will spread out into various other sectors. So loath I am to suggest that this might be a rich vein for the legal profession. Anybody in the audience wish to add to that in terms of what the panel said? If anybody else wishing, Peter.
Just to add to your points, Martin, on the reliability, one of the things that concerns me as a rather aged engineer is looking at the automated cars and so on, and wondering, are they going to be tested in the same way as as the sort of conditions that you encounter in country lanes with potholes, and they're tested on idealistic roads. I mean, when the military take a piece of equipment, it's plus 50 to minus 30 or whatever it is, and all the various levels of ruggedness, as well as the cyber security and the validity of the data. That's all got to work in the real life physical conditions as well.
No, I think the answer to that is I hope so. Jonathan, you put your hand up, I think. We've got, just whilst the microphone's making its way, we have a few more minutes, but if you've got any questions, please raise your hands now so that I can work out how many we've got.
Different sort of question. I wanted to pick up on the training needs question. Are universities currently producing the right kinds of people with the right kinds of skills to contribute to the kind of things we've been talking about? Do we need new undergraduate degrees, master's degrees, conversion degrees for people in other disciplines? What would the panel recommend?
So, in brief, my answer would be no. I don't think. If you look at innovation and growth strategy, and you look at the growth in business that's predicted in that, I don't think that the sector, I don't think you just aimed at universities, are producing the volume of people that are needed. So that leads me to a different areas. I think that one of the areas that we need to grow in is reskilling people. We have a skilled workforce, but there is elements where we need to reskill that workforce to meet that need. There's no doubt also that we've done some market work looking at the future of the business, and there are areas in this space-enabled services sector where we need a new type of scientist, a new type of engineer to really drive those services forward. So I think there's a number of failures there, actually. I think that we aren't producing enough of a volume, and that's not just wholly at the universities. It's actually, I don't know if industry are making it clear enough what skills they want and getting students excited enough so they can see the career opportunities to draw them through. I think the rate of growth is going to outstrip supply anyway, and I think therefore we've got to grasp the nettle of reskilling in order to reach that. So I think there are a number of potential failures that could really be a barrier to growth if we don't address them in the short term.
And if I can add on a hobby horse of mine, and that I think is that we have to be very careful how we structure that education, that we should be very careful to educate with very clear fundamental knowledge, and then add specialisms, because specialisms go in and out of fashion very rapidly. It's very difficult for the education system to respond to that. It goes through a low-pass filter, so quite often it can easily get out of phase. So what we need to do is make sure our education system gives a very sound basis of mathematics and physics and all the relative, and indeed it will probably move off into biological sciences as well in the future, so that there is that sound understanding on which you can then add the icing of specialisms, and universities and schools can adapt that a little bit more quickly. But I think it's a big mistake to for certainly the tertiary education sector to try always to be linked into the latest fashion in industry and applications. Some very good examples of that is where 10 or 15 years ago, power engineering vanished from university syllabi, only to re-emerge now because we've got big power problems in the microelectronics industries. So I think we have to be very careful to how we structure the education program. So hobby horse over. Anybody wish to add? Craig.
Actually, my experience from recruiting in Glasgow is actually we don't really have a problem with recruiting the right people. We're quite lucky in Glasgow. We've got two very strong universities in the engineering side, but they are attracted to Clydespace because we are in the space industry. So it makes it a bit easier in this industry to attract good quality graduates into the business. But I think generally speaking, though, we don't have enough people going into engineering and the STEM subjects. And I still hear all the time that our brightest children are choosing accountancy, and it's actually quite good that we're in the Royal Academy of Engineering to discuss this point, because the engineering community need to do a lot better. It's showing children what a career in engineering can lead to, or similar sort of STEM subject careers. Even the CEO of Scottish Enterprise, who understands completely the need for more children going into STEM subjects, her daughter with an A in physics is now doing accountancy. So I don't know if there is a Royal Academy of Accountancy, but they must be doing a good job of recruiting people into that area. But we need to do better, just generally as an industry, to do that.
Can I add something on the government side? Sorry, I think I won't comment on the sort of industry side, but certainly in government, I think there's a desperate need for more people amongst bureaucrats and officials who understand space and what space has to offer. There's been, I would liken it to people who can understand ICT properly, for example. I think, there's a sort of aging population of government specialists in the space sector. And one of the things that we're encountering is a real sort of desperate need for officials who can really get to grips with space and what it can offer government, and who can also speak to industry and really understand what the growth opportunities are, what the science opportunities are, and so on. So it's something we're giving very active consideration to, sort of shorthand a space university for government, because I think it's really needed. I think we need to be sort of speaking a common language and really understanding how we can exploit this. And this sort of thinking is getting real traction in our conversations with, for example, the European Commission, who also recognise that they could be doing a lot more to promote the use of space, both as a means to make government more efficient and effective, but also in terms of how it then feeds through to good regulation and all those other things which government at various levels is responsible for.
I think one of the things that's really interesting is space is very multidisciplinary. You can almost find a challenge that's applicable to almost any engineering course and find some relevancy within for that to the space. It's also very attractive as a construct, so people are excited by the opportunity. So I think it's actually beholden on us to create the materials that allow the universities and the STEM ambassadors to really to actually create an awareness of how do you use your technology in space and see how it brings value. I think the other aspect here, when we're recognising all the way through today that actually 80% of the growth is in the downstream, if we haven't got the markets which we can really address, access, then we haven't got a future. And many of those aren't specifically engineering, but there's very high demand for software skills, for the understanding of data science, etc. So I think, again, if we're looking at how do we create awareness during that education process so people take that knowledge with them through the rest of their careers, we've got something we could actually bring to the table, and we should try and do so.
Can I finally reinforce the point that you made? I was talking to a computer science teacher the other day, a university lecturer, and they said, you know, some courses went down the line of teaching X language, and the language that is popular in the computer sector changes about every 3 years. You can think about it: Python, R, Fortran, Pascal, C++. You know,
now you're showing your age.
Oh, I'm showing my age over the latter ones, but it's changed on about a 3-yearly basis. So the point of teaching a given computing language changes with the firm, but actually understanding how to code and how to understand and to derive value from that is the fundamental skill. So I'd like to reinforce Martin's point, really, that it's about having those fundamental skills that enable a sector.
Yeah, thank you very much. And I think just coming... Sorry, do you want to say something? No. I think just coming back to the point that was made by Catherine, that we've talked a lot about the exploitation of space for business and related areas, but a very critical part of space is actually making sure that government can make a coherent exploitation of everything that space and its consequences can offer it, and to ensure that, first of all, that our government exploits it to the full for the benefit of the population, but also is agile and has a finger on the movements within the commercial sector, so that we can get policies and regulations that, first of all, sensibly support the commercial sector, but also help drive our prosperity agenda. And I would be interested, just in the sort of closing minutes, whether to ask a question back to the audience as to whether there's anybody in the audience who feels that there are policies or regulatory issues that should be addressed more urgently or more fully, or maybe even different ones that are not being done so at the moment.
Sorry, this is another trivial comment. I wouldn't mind to know how many in this audience has filled out a PSS form for ESA. And would you like to see it revised in some form? I find working for ESA and the level of bureaucracy that comes out of Europe, for a small business employing 50 people, and not primarily in space as an instrument business, are very frustrating activity, and that's an area which the UK government could very much address upon the SME's behalf.
Thank you very much. And as we have a new Director General of the European Space Agency, it's an ideal opportunity for this question to be posed. Yes, sir.
Yeah, picking up on your hobby horse of people should learn the fundamental skills. Personally, my hobby horse will be that universities need to start, increase and improve the innovation skills in education, because I think that more than anything would help us innovate in the space industry and indeed others.
Okay, while we're on hobby horses, if you indulge me one more, and that is that, again, we have to be very careful about teaching specific technologies. We do need, I think, to increase our teaching of systems engineering, because what we're seeing now is not only, obviously there are great advances in individual technologies, but it's increasingly bringing these technologies together to provide very complex systems, both hardware and software, and understanding how to manage systems as well as individual technologies, I think, is going to become even more critical. Sorry, so I should only allow myself 3 hobby horses.
While we're on hobby horses, you seem to have a whole team of them. You talked about skills and the need for more graduates in STEM, but it's a stubborn fact that most STEM disciplines, physics, chemistry, biology, mathematics, computer science, most disciplines of engineering, have higher than average levels of graduate unemployment. As in the graduate unemployment rate 6 months after graduation is higher than the national average for all disciplines. How do you reconcile the fact that industry is obviously crying out for more people, yet somehow these young people who are trained are not finding the jobs that they need and that you want them to have?
Very interesting statistic, of which I was previously unaware. Does anybody have any further information or views on it? First of all, from the audience, Richard.
Yeah, I think if you take a typical STEM graduate and industry is looking at employability, then the communication skills become important, and if you can't communicate properly, usefulness is limited. And we talked about complex systems and multidisciplinary systems engineering. part of that system is the people. So the more we can actually give people the communication and people management skills, the better we're going to get at innovation. Innovation is a sort of probabilistic activity. You need to have the right, increase the chances of having the right set of people in the right place at the right time to address a particular problem. And the key to them achieving a solution is communicating and understanding each other.
Thank you. Craig?
I think that this probably comes down to some people feel that they need to go to university when maybe they shouldn't be going to university. There are other ways of becoming an engineer or working in engineering without having to do that. So, I mean, if you are exceptionally good in your course, you will get a job, no question about it. But if you don't perform as well at university, maybe it's not quite for you, then you're going to struggle. But there are lots of apprenticeship schemes that you can go in specifically for the space industry as well. So if you're coming out of school, you can join an apprenticeship scheme and go through college and actually go through university. It's a better route for some people, or come into the space industry in a different discipline. But I think university isn't the answer for everybody, and I think that's probably why what we're saying. Can I come back to my previous point? Our bright kids are not going into engineering. If I had more bright kids going into engineering and biology and physics, then we would see more people getting jobs from that. So I think another point is it'll come down to kind of fundamental education. You can still do accountancy if you do engineering. You can't do engineering if you do accountancy. So I think engineering and physics and maths are a good foundation for lots of different disciplines. So you need to get more kids doing that to give them more options.
Thank you very much. Well, I noticed that's brought us to click over exactly the 5:30 mark, and so I wouldn't want to keep you from looking again at the exhibition and with the added enticement of some drinks alongside that. So I would very much like to thank all of today's speakers and the audience for questions, and the panelists who have, I think, had a very interesting last hour. And just to say that there will be a short report that will be published a bit later on this year on the Academy website. And of course, this is just one event in a series, which started back in 2012. And there have been events on construction, automotive, medical technologies, materials, energy, aerospace, autonomous systems, agri-tech. And there will be another of these events that will occur fairly soon, so please keep your eye open on the Academy website for notice of that. And I do hope that everybody in the audience has enjoyed the afternoon and found it interesting and useful. And if you've got any suggestions on how these could be improved, please feed them back to the Academy. And I would like you just to thank our panelists here, and then my last job will be to invite you downstairs to join the reception, and you can have another look around the thing. So thank you very much indeed, and thank you to the panelists.